Hello, good morning, everyone. We will start in a few minutes. Okay. Hello, everyone. Good morning. How's
Good
everyone
morning,
today?
sir.
Ayan. Are you all ready to defend your thesis proposals? Okay, so welcome to parallel session 2 for this morning. So we have six presentations for this morning. So our session chair will be Dr. Terence Tomolva. I'm Michael Shonde. I'll be your host, and we have our panel assistant, Engineer John Nico Salvilla. So for this parallel session, we have four groups under Dr. Jude Michaela Berilla, and we have two groups under Dr. Joey D. Hakon. All right, so 30, ready? Ayan po. Wait lang. Before we start pala, just some house rules. Okay, so kita ba yung house rule slides? Okay, so for our house rules, so just keep taking of the following. So please mute your microphones and turn off your cameras while presentations are ongoing. Your uploaded YouTube presentation will be played during your time slot, and then a live Q&A forum will follow around 5 minutes siguro. And then everyone may ask questions during the meeting's chat box and will be read out for the presenter during Q&A. If you have any questions, you can also ask them live by raising your hand, okay, during Q&A and wait to be acknowledged before unmuting. Whenever you're asking a question, please turn on your cameras. And please take note, this is being live streamed via YouTube and being recorded, so please observe proper behavior. So that's it, and good luck to all presenters for today. And so for the presenters din pala, please prepare your slides and you may also share your slides during Q&A. Ayan, so I will be making you co-host every time for every presenter. Ayan, so without further ado, let's welcome our session chair, Dr. Terence Tamolva.
Okay. Thank you very much for that introduction, Sir Mike. And good morning to everyone. And welcome to session two of this this colloquium for 2021. Okay. So without further ado, let's start with the first group under the advisement of Dr. Jude Michael Aberilla. And that group is composed of Mr. Martin Carlo Belen and Mr. Andre Esteban, and their thesis title is Comparison of Environmental Impacts of Air Purification Technologies Using Life Cycle Analysis. So, Mr. Belen, Mr. Esteban, you now have the floor.
Okay na, sir. Ay, mag-play ng YouTube. Technical difficulty lang.
Good day, everyone. I'm Andre Esteban,
And I'm Carlo Belen.
and it's our pleasure to introduce to you our proposed study entitled Comparison of Environmental Impacts of Air Purification Technologies Using Life Cycle Analysis. Anthropogenic activities are considered as the major cause of environmental air pollution. Furthermore, other basic activities of daily living were also found to contribute substantially, particularly to indoor air pollution. Activities like cooking, smoking, use of electronic appliances, and use of consumer products can release harmful pollutants. According to the World Health Organization, indoor or household air pollution was seen as the main cause of 3.8 million premature deaths every year. Three main strategies are used to address indoor air pollution. First is source control, which is recognized as one of the most effective methods as it directly considers the elimination of pollutants right from its source. Second strategy is through effective ventilation, where a system of exchange of air flowing in and out of a closed space is being established. In recent years, another strategy which involves air purification technologies through various filtration media has been considered in addressing indoor air pollution primarily due to its high efficiency in purifying polluted air.
With the issue of indoor air quality in mind, air purification technology is the strategy that is widely used within homes, offices, and other indoor settings to clean the air people breathe in. There are many air purifiers commercially available in the market, with brands in the Philippines including Philips, Sharp, Daikin, and more. These technologies employ various techniques such as filtration, adsorption, and electrostatics that tackle different pollutants based on their capabilities. The major pollutants they tackle are particulate matter like dust, volatile organic compounds or VOCs, and microorganisms, particularly bacteria and viruses. There have been many studies expanding on the capabilities of these techniques in air purification, as well as ways in which they can be further improved in terms of both effectiveness and efficiency. However, despite the studies on these various air purification techniques having been extensive, there has not been enough research comparing them in terms of their sustainability. This becomes a problem considering that further developmental research must be equipped with sustainable production in mind as the world becomes more and more affected by pollution. Researchers must be informed of what road may be taken or what must be focused upon for air purification towards sustainability. In line with this, one way to assess the sustainability of these technologies is by using the life cycle analysis methodology, or LCA. Through LCA, we can measure the environmental impacts of a technology by accounting for all of its inputs and outputs across all stages of its life cycle, from material sourcing, transportation, production, distribution, usage, to disposal. The LCA methodology is widely used and recognized in governments and industries and has been applied in the study of many different technologies. For air purifiers, only two studies were found to have applied LCA, and these were limited to assessing only their particular devices. None looked at the different air purification techniques. The application of LCA in this study will allow us to assess the sustainability of air purification technologies in a systematic and objective way. Apart from assessing this, it would also be of interest to study the possibility of local sourcing and production for air purification, as this may entail an overall more sustainable consumption of air purifiers in the Philippines. With this, we may look into zeolites, which are locally mined aluminosilicate materials whose structure allows them to act as adsorbents. These are also used in commercially available air purifiers and are common in developmental studies that focus on adsorptive air purification, as well as for improving the performance of integrated air purification technologies. Thus, this study shall assess the environmental impacts of different air purification technologies by using the LCA methodology following a cradle-to-grave approach. Specifically, the impacts attributable to the different air purification technologies shall be compared while considering when these techniques are combined in some devices. It shall also assess the potential of sourcing natural zeolites for local production of air purifiers in terms of its potential environmental impact. The data collection for this study shall be limited to existing databases and data from commercially available air purifiers, as we'll be discussing later. Findings for this study shall be appropriated to the Philippine setting, especially with regard to the environmental impacts of transportation.
The results of this study will be valuable in designing and producing more sustainable air purification technologies, directing future research, implementing relevant policies regarding the production and use of the air purifiers, and benchmarking the sustainability of local production of zeolite-based air purifiers. Shown here is the framework of life cycle analysis, which will be the method used in the study. First, we have the goal and scope. This study will provide a comparison of the different air purification technologies, their environmental impacts, and sustainability using the LCA method. The technologies that will be studied include HEPA filters, adsorption, electrostatic precipitation, photocatalytic oxidation, and plasma purification. In the lifecycle inventory phase, existing databases such as the commonly used EcoInvent database shall be examined to determine which data can be used. Dismantling of air purifiers may also be done if the data initially gathered are not sufficient. In the lifecycle impact assessment stage, the recipe model will be the method used in analyzing the environmental impacts. The main goal of the recipe method is to translate a long list of emissions, resource extractions, and other inventory results into a limited number of environmental impact scores. Interpretation of these data will be iterative to ensure that the results are analyzed in the context of the goal and scope and to give proper recommendations.
Here is our tentative schedule. We may begin collecting data from available databases by July to determine what other data will be needed that may be collected from actual air purifiers, after which we will procure and dismantle them to collect data. Much time is allotted for this in case of any issues with procurement. After we have gathered the needed data, we can proceed with inventory analysis and impact assessment, from which we can gather results and begin writing the final manuscript. A lot of time is allotted again for manuscript writing and revision in case we will need to collect or analyze more data for the study. Upon canvassing air purifiers online, the cheapest applicable air purifiers we found were at around 12,000 pesos each, so our current estimate for two air purifiers is at 25,000 pesos. Tentatively, we will need to procure only 1 to 2 air purifiers as we need to see their contents and how much zeolites would be needed to replace the current amount of the other material, such as activated carbon, that is being used. However, we will need more air purifiers in case our initial data collection falls short of what we need, such as if a particular air purification technique does not have data. With that, thank you very much for listening to our presentation. We hope you can look forward to our study next semester. Thank you!
Thank you, Mr.
Okay.
Esteban and
Yeah,
Mr. Belen.
thank you, Mr. Esteban and Mr. Sorry. Yeah, tama. Mr. Esteban and Mr. Belen. Are there any questions from the audience? Wala. Okay. So, oh, there's a question. from Miss Christiana Calderon. Yes?
Hello po. I'd like to ask the group, how did they choose the technologies for like the air purifier?
Okay, so I
So
think
how
I
did
can
they choose the
answer that.
question?
Okay.
Again, Mr. Belen.
So, if it's regarding the classifications of the air purification technologies that we discussed earlier, yung five main types na filtration, adsorption, electrostatic precipitation, photocatalytic oxidation, um, and plasma purification pala. Yun kasi yung main talaga na technologies na ginagamit in air purification. Tapos with regard naman dun sa possibly i-procure namin na air purifiers, we chose those na mako-compare namin siya to para kapag magsa-source kami with zeolites. Kasi 'di ba with LCA, you look at the raw materials then. And one methodology that we found if we want to see kung may potential tong other raw material is parang i-compute namin what if i-replace namin yung raw material na nasa existing air purifier with this raw material na zeolites. So that's how we came up with na dalawang air purifiers.
Hello. Naririnig mo ba?
Yeah.
Yeah. So to add to that, in choosing the technology or the air purifier na i-acquire namin, first tiningnan namin what are the different techniques that are used by air purifier brands. So usually there are a lot of techniques that are integrated into the air purifier. So like for example, it could be a combination of filtration, absorption, catalytic oxidation, or other combinations. So like we chose we are choosing, or we are currently narrowing down the air purifiers that we're gonna use based on the available techniques that are integrated dun sa specific model ng air purifier. Ayun.
Okay, just to be clear, Mr. Esteban and Mr. Belen, your technologies, the technologies that you chose or will choose are intended for purifying indoor air, tama?
Yes, sir.
Yes, possible.
And you found existing technologies kasi you mentioned electrostatic precipitator. These are things that are also used in industrial plants for treating their air pollution emissions, right? So for your case, you've actually found indoor air purifiers that use electrostatic precipitators, ganon?
Yes, sir. We found these naman in existing na air purifiers. At first, nakita lang po namin in literature na ginagamit siya ng different brands from different countries. And upon searching then ourselves sa units or models na available in the Philippines, we found na meron din gumagamit ng same technologies used industrially, pero smaller scale.
Okay. And all of these technologies that you will choose to compare, all of them allow for substitution of the zeolite adsorbent, kasi that's one of your diba, of your specific objectives, that you want to investigate what will happen if you use the zeolite. Tama? Pero kasi like for example, electrostatic precipitator, gagamitan ba ng adsorbent? Ng zeolite yung technology, di ba? Hindi. So, I'm interested in knowing how you will proceed with the comparison. Kasi it's one thing that you have all of these technologies, tapos they all have a specific adsorbents, tapos lahat sila papalitan mo ng zeolite, diba? So medyo the substitution is across all the technology. So yung comparison ninyo parang merong solid foundation. Dito yung iba pwedeng gamitan ng palitan ng zeolite yung iba, hindi pwede. So, how are you going to proceed with that? Medyo lopsided yung magiging comparison,
Ah,
diba?
okay. So sir, with regard to comparing yung sa zeolites, i-compare lang din po namin siya to air purifiers na may
At least
adsorptive technology.
absorbance.
Yeah, like doon lang
Okay.
po namin i-compare yung sa zeolites. Pero other than that pa yung pagko-compare namin across all of the five technologies kasi we recognize naman na hindi applicable yung zeolites in all of them. So medyo hiwalay po sila. But then again, since nga na-integrate yung air purification technologies in the air purifiers, it could be part of the comparison then, pero not necessarily to replace yung functions ng like electrostatic precipitation or photocatalytic oxidation. Parang gagamitan na lang ng allocation with regard to that within the LCA methodology.
Sige, I have many more questions pa, pero we don't have time. I look forward to seeing your final thesis next semester. Ayan, it's very interesting, especially knowing what LCA tool you're going to use and how you're going to factor in pricing and costing analysis. Okay, so thank you very much to the first group. Now let's proceed to the second group. Still under the advisement of Dr. Jude Aberilia, and the group is composed of Ms. Sheen Pampola, Mr. Emerson John Ramos, and Ms. Kenil Denise Zerna. And the title of their thesis proposal is Sustainability Assessment of Resource Recovery from Municipal Solid Waste in Metro Manila Cities. Okay, so GMA 2, you may proceed. JMA.
Good day, everyone. In partial fulfillment for the requirements of Chem E 143, we are JMA 2, Shini Pampola, Emerson John Ramos, and Kainil Denise Zerna, presenting to you our proposal entitled Sustainability Assessment of Resource Recovery from Municipal Solid Waste in Metro Manila Cities. Metro Manila, as the center of economic, social, and cultural activity in the country, is among the most densely populated regions in the world. High levels of urbanization and increase in population has caused the swell in the volume of waste generation, with adverse effects on human health and the environment. In 2010, the average per capita per day generation rate of the Philippines was 0.40 kilograms, while for Metro Manila and highly urbanized cities, the rate was 1 kilogram per capita per day. Based on this rate, the yearly amount of waste is projected to increase from 13.48 million tons in 2010 to 18.05 million tons in 2020, while Metro Manila's contribution to this amount is projected to increase from 22.2% to 26.7% within the same timeframe and more so in the years to come. According to a study by the Environmental Management Bureau, from 2008 to 2013, 56.7% of municipal solid waste generated is attributed to domestic waste from residential areas. Of this, the breakdown of the total waste composition in Metro Manila is shown in the figure. Food waste and plastics comprise more than half of the total waste, which reflects the consumption trends and can be used as basis for solid waste management schemes. In the Philippines, landfilling is the predominant waste management strategy. However, only 21% of LGUs have access to sanitary landfills. Of this, a total of 186 sanitary landfills from 407 LGUs nationwide are currently operational, aside from the informal landfill sites. With the waning capacity of landfills, diverting solid waste and converting them to valuable sources is now an emerging priority.
With the vision to improve solid waste management in the Philippines, the government has implemented several measures to protect public health and safety against hazards brought by wastes. One of which is the Comprehensive Republic Act 9003, or the Ecological Solid Waste Management Act of 2020. The allocation for solid waste management is estimated to reach 3 billion pesos every year, while RA 900 requires the diversion of at least 25% of waste away from landfill sites. Waste management strategies in the Philippines are still predominantly landfilling. With this, waste management schemes present a great potential to divert from the usual landfill scenario. LGUs have introduced materials recovery facilities or MRFs, encourage segregation at source, composting, and recycling practices. These waste diversion methods are able to convert solid wastes to valuable resources. The general goal and objective of this research is to evaluate the sustainability of resource recovery methods for municipal solid waste in Metro Manila. Specifically, it aims to identify resource recovery frameworks currently in place in the region, assess the environmental impacts of current municipal solid waste management systems, under which is to assess the volume of resource recovery in MRFs, recycling, and composting facilities, compare the magnitude to waste deposits in landfills, and lastly, to evaluate the environmental potential of the different resource recovery scenarios as a municipal solid waste strategy. For our methodology, we will be using Life Cycle Assessment or LCA. This tool represents a promising solution in assessing the environmental impact of municipal solid waste management. The four main parts of this process are the following: setting the goal and scope definition, performing an inventory analysis, assessing the environmental impacts of the input, and finally, interpreting the data we have come up with using a life cycle analysis software. In setting up the goal and scope definition, a cradle to grave approach will be implemented. The researchers must be able to compare the environmental impacts of composting and recovering through MRFs with landfilling. The system boundary shown in the slide is already defined. It all starts with a collection of municipal solid waste and includes waste transport, waste treatment recovery technologies, and landfilling. The input comprises all raw materials and energy needed to perform each stage, while the outputs are recovered materials, fertilizers, and waste and gas emissions. In dealing with byproducts in a complex waste production system expansion will be done by broadening the process of the byproducts and by determining their secondary purpose. Additionally, allocation will be performed to model the indirect results of variations in the material input for processes that produce byproducts. Densely populated urban areas generate large volume of municipal solid waste per capita, with standard deviations relatively lower than those of urban areas, making them applications for studying the sustainability of resource recovery for municipal solid waste. Thus, the cities in Metro Manila will be our research interests. The study will cover the prominent fractions of Metro Manila wastes and their constituent waste-to-material resource recovery methods. Specifically, composting will be considered for food and organic waste, while recycling and materials recovery facilities will be considered for plastic, paper, and glass waste.
Data processing will be performed once the goal and scope of the study have been set. It starts with data collection and includes life cycle inventory analysis, impact assessment, and interpretation. Solid waste data for biodegradable, non-biodegradable, and recyclable waste will be acquired from the Environmental Management Bureau of each municipality. These data include, but are not limited to, waste categories and fractions, solid waste management, and waste diversion plans. Databases of resource recovery technologies will be obtained from community environment and natural resources, municipal solid waste offices, and private institutions in Metro Manila. In inventory analysis, the inputs and outputs of each process will be identified using the material and energy flow passing through the system boundary. This input-output will be characterized to aggregate their contributions to each impact indicator. In performing the impact assessment, the recipe model and EcoInvent database will be used, and data will be simulated through the OpenLCA software. The quantitative results obtained from impact assessment will be evaluated and interpreted to compare the environmental sustainability of each scenario: composting, MRF, MRF to landfilling, and landfilling. The 16 impact categories that will be used in this study are global warming potential, ozone depletion, ionizing radiation, particulate matter formation, photochemical oxidant formation potential for ecosystems in humans, terrestrial acidification, freshwater eutrophication, humotoxicity, terrestrial, freshwater and marine exotoxicity potential, agricultural land occupation, water consumption, surplus ore, and fossil fuel potential. For the expected results, functional units of biodegradable, non-biodegradable, and recyclable waste processed in composting and material recovery facilities will be quantified as kilogram of fertilizer per kilogram of biowaste and as material percent recovery. These will be used to identify the contribution of composting and recycling in decreasing the volume of waste in landfills and dump sites. Moreover, the environmental impacts of each scenario will be interpreted through the characterization results of the impact category. The latter half of the study includes database gathering, inventory simulation in OpenLCA, impact assessment and interpretation of data, and finalizing the manuscript. The researchers have started the database gathering and will resume in the third week of August. 3 weeks will be allotted for interpretation due to possible revisions in the model, data, and assumptions. If you have any questions, feel free to message us through the emails shown on the screen. Thank you for listening.
Good day, everyone. We present to you our thesis proposal.
Okay, thank you very much to the second group. The floor is now open for questions from the audience. Yes, Miss Calderon.
Hello po. Would like to ask, why did you choose Metro Manila? Like, do you mean that the waste is in Metro Manila or like the recovery in Metro Manila? Why there? Why not Philippines?
I'll answer this na lang po. So actually, all the data will be coming from the solid waste management reports in Metro Manila. Kasi po, upon preliminary findings, we found out that in all the cities in the country, the region's solid waste management was better documented compared to other areas in the country, which makes it easier for us to collect data, allowing us to focus more on the data treatment. And aside from that, we believe that the increasing population density of NCR can lead to a lot of environmental and economic problems, thus the need to allot our focus to these areas more. But there's also a potential to make these data appropriate to other regions in the country as well. Thank you for that question.
Okay, thank you. Are there any more questions from the audience? Okay, so just to clarify, you have access to all those reports that you cited in your presentation?
Yes po. Nag-start na po kaming mag-collect ng mga data per city and meron naman daw po silang data on that.
And the latest report was published in 2000.
The latest po is around 2019. Tapos meron pong data na from 2015 and we consulted our research advisor about that and sabi ni sir po na parang if wala pong data na available for the most recent one, so we'll just lang po, use trends, use the data from previous from the latest report para we could infer na lang on the possibility kung ano yung na-produce in the latest years po, parang gano'n.
Yeah, okay. So I think that's one of the limitations that you have to cite in your thesis. Okay. Also, I wonder how, for example, there's a variation in the years of reporting. Like you need several reports, pero one report for this particular set of data is in 2019, the other is 2020. How are you going to consolidate that? So that is something that you have to take into account also. Huh? Sige, one final question. Can you give us a preview on how you're going to conduct the energy flow analysis? Kasi material flow, madali lang. Diba? Ano lang yun eh. As in, it's material. So you just have to track where the solid waste goes. Pero energy requirement and energy consumption is different. Diba? It's not just from the different points kung nasan yung materials. It's also involved in the transportation and the processing itself. So how do you tend to measure how much energy is being used?
Ayun po sir, based po dun sa system boundary po namin, we have identified yung elements po na nagko-comprise po in computing for the energy balance. So we will just make sure na we take into account everything from the collection of waste to the transportation to the amount of energy that will be produced for waste to material technologies and up to the final stages po of the life cycle analysis of the wastes po. So we'll also use literature references to make sure that we tackled our findings are comprehensive para complete po yung findings namin.
Okay. Sige. Maybe I'll just wait for your final report because I'm interested to know, like, for example, how you're going to take into account how much energy is consumed by the transporting of solid waste from one point to another, kung truck yan, depende sa size ng truck, diba? Those,
Yes,
and then the processing, separating the different components in the MRF. Anyway, sige, I look forward to seeing your final report as well. Okay, thank you very much to the second group. Now let's proceed to the third group of Dr. Judah Virilla. And the duo is composed of Ms. Doreen Sueybagio and Ms. Elaine Pasion. Okay, and the title of their thesis is Uncertainty and Variability in LCA and LCC of Solar PV and Wind Turbine Technologies in the Philippines. Okay, so Ms. Sueybagio, Ms. Pasion, you now have the floor.
Good day, everyone. We present to you our thesis proposal entitled Uncertainty and Variability in LCA and LCC of Solar PV and Wind Turbine Technologies in the Philippines. To start, let us look at the context of the energy situation in the Philippines. From 2018 to 2019, a 44.7% energy price increase was reported. This was attributed to the slow development of new energy sources to accommodate the rising demand. Thus, seeking new energy sources is being done where renewable energy is considered a prospect. In 2019, a report by the Department of Energy showed that non-RE sources dominated the country's energy mix, comprising 70%. Now, if majority of our energy sources continue to come from non-renewables, the power sector would continue to be the greatest contributor to the country's carbon emissions, which is also the largest driver of climate change impacts, such as extreme weather conditions. Therefore, this dependency on non-renewable energy will not only result in scarce energy sources, but irreversible damages to our ecosystem as well. This poses a problem for a country that is prone to natural disasters. To produce new energy capacity that sustains economic growth while mitigating climate change impacts, utilization and commercialization of renewable energy sources are implemented. One of the country's actions is the National Renewable Energy Program, or NREP, which seeks to triple the RE-based capacity of the country from 2010 to 2030. The country's comprehensive policy and regulatory framework sustains positive interest from investors. However, the NREP falls behind the technological aspects to accommodate the surplus of renewable energy applications. But what makes renewable energy hard to deal with? Renewable energy technologies like solar and wind are heavily dependent on weather and climate conditions. With this, energy generation becomes highly intermittent and location specific. This leads to a variable characterization of its economic feasibility and environmental impact. This uncertain, variable, and location-specific nature of renewable energy reduces its economic appeal due to the greater exposure to downside revenue risk compared to that of traditional energy sources. In addition, this makes the analysis of its environmental impact somewhat inconclusive, given the wide range of possible values that is generated. This information is important in decision making, especially for policies. Before we move on to similar studies, let us first define life cycle analysis and life cycle costing. Life cycle analysis is a useful method in analyzing environmental impact. In simpler terms, it is a method to evaluate the sustainability of a product or a service by calculating the emissions associated with its life cycle. LCA has the following steps, which we will discuss further in our methodology. On the other hand, a similar method called life cycle costing is used to evaluate the economic cost associated with a product or service. The process includes the same steps with life cycle analysis, excluding the impact assessment step. Also, for LCC, instead of emissions, we account for the economic cost in each process of the life cycle. Now that we have an idea of LCA and LCC, let us look at similar studies which you can access through the QR codes that are shown in the screen. In the study by Pade et al. 2013, they presented a methodology to provide a comprehensive and accurate life cycle assessment as compared with literature. They reduced the input variables by applying global sensitivity analysis or GSA to determine the most significant parameters in LCA of onshore wind turbines in Europe. Furthermore, a study by Tran and Smith in 2018 compared the variability and uncertainty of energy costs in the US. They applied GSA on levelized energy costs, a metric which is useful in measuring commercialization feasibility of the technologies. Going back, let us remember that RE technologies are location specific. Thus, the gap our study aims to address is the application of GSA in the Philippine context, since other studies mostly cover Western regions. Furthermore, the side-by-side analysis of environmental impact and economic cost of renewable energy technologies is expected to be more insightful in forwarding RE projects than when they are separated. With that, the objectives of the study are to evaluate the environmental impact and economic cost of renewable energy life cycle, then subject these evaluations to sensitivity analysis to understand the variability and uncertainty of solar PV and wind turbines in the Philippines.
Given our objectives, the next question is, how do we plan on achieving them? And for that, we present our proposed methodology. First, we have our goal and scope definition. For our study, we will focus on the Philippine geographical context and investigate existing and emerging technologies in the country. In particular, we will focus on crystalline photovoltaic and thin film modules under solar PV technologies and both horizontal and vertical axis wind turbines under wind turbine technologies. Next, we set 1 kilowatt hour of electricity produced as our functional unit. This quantity will serve as the basis for our material and energy balances later on. Lastly, our study will cover life cycle profiles of solar PV and wind turbine technologies from cradle to grave. This means that all input and output streams will be considered, from equipment production to installation to operation and maintenance to disassembly and finally to the system's end of life. That's it for goal and scope definition. We now move on to the identification of reference models. For the LCC, we will use a modified LCOE equation adopted from a research by Tran and Smith 2018. In this equation, LCOE stands for the levelized cost of electricity and is a function of both total annualized cost and annual electricity production. For the LCA, we will adopt the greenhouse gas performance equation from a study by Pade et al. 2013. Here, the global warming potential is a function of the greenhouse gas emissions and the total electricity produced by the system over its lifetime. If you want to check out our sources, you may scan the QR code on your screen. It is worthy of note that the parameters in these equations are variable and therefore have variation ranges and statistical distributions. In line with that, the next parts of our methodology are two closely related steps, which are data gathering and life cycle inventory. In these steps, we will perform material and energy balances for the input and output streams relevant to the system boundary we set. We will also identify the statistical distributions of our variable parameters. All of these data will be obtained from manufacturers' databases, commercial databases like EcoInvent, Lazard, and EIA reports, and existing literature. Once we get all necessary data, we will now proceed to the last two steps of our methodology. From the input statistical distribution, we will perform the Monte Carlo simulation via CIMAPRO to get an output distribution. And what the Monte Carlo simulation does is to generate random combinations of values from the input distributions and to plug in that combination to the reference model to obtain one output value. Let's take the case of our LCC reference model as an example. A random value from each of the variation ranges of the variable parameters here will be generated and combined to solve for the LCOE value using this equation. This is done for another combination of values for up to thousands of iterations to yield the final output distribution. For our study, we chose to go for 10,000 runs, which is a reasonable number that can be handled by the software without compromising our goal of getting a wide range of outcomes to get accurate and consistent results. The same process will be followed for LCA. It is important to note, though, that the recipe method will be used to quantify the greenhouse gas emissions term in our equation. And what is this recipe method? The recipe method is a widely used life cycle impact assessment method, which classifies our input and output streams into environmental impact categories and returns a final GHG emission score. After obtaining the output distributions, we will perform the global sensitivity analysis to meet our goal of identifying the parameters most influential to the output distribution's variation. And to do this, we will use the Sobel indices. In simple terms, the parameter which yields the highest Sobel indices is the most influential to the output variance. Now, there are two types of Sobel indices. The first order Sobel index measures the contribution of a variable parameter to output variance, independent from its interaction with the other parameters. On the other hand, the total order index considers the interaction of the parameter with the other parameters. And for this study, we will calculate both indices for each parameter. The result of the GSA will look like the graph seen on your screen, with parameter 2 being the most influential parameter to output variance. Once we identify the most influential parameters, what can we do with that information? The identification of variables most influential to LCA and LCC variability could be a strong basis for renewable energy development projects in the country for two possible ways. Number one, RE development projects may focus on improving these parameters. Second, these results may be used for developing simplified models, which could lead to a more efficient assessment of the environmental impact and energy cost of a proposed energy project. Both of these ways could be instrumental in confronting one of the country's greatest barriers to renewable energy deployment.
Now that we have established our goals and methods, we present our proposed timeline of activities spanning from July to December 2021. That concludes our presentation, and thank you so much for listening.
Okay, thank you very much to the group of Ms. Suey Baguio and Ms. Passion. Okay, so the floor is now open for questions from the audience. Yes, Ms. Eusebio.
Good morning po. My question is, why did you choose the Sobel indices for your global sensitivity analysis?
Good morning. I'll take this question na lang. So the Sobel sensitivity indices is a variance-based method which has been used across many LCA studies that we were able to encounter in our literature review. And this is mainly due to its ease of interpretation. As we showed earlier in our presentation, the graph produced from using Sobel indices is very straightforward, as you only have to look at the parameter which yields the highest Sobel index to know the parameter most influential to output variance.
Adding to what Doreen said, the Sobel indices actually enable us to separate the variance caused by an individual parameter and its interaction with the other parameters. So it gives us a more complete analysis as to how the parameters actually contribute to the variance of the output value.
Okay, are there any more questions? Ah, yes, sir. Hi, sir. Pwede po magtanong kahit hindi batchmate. Yes, go ahead. Mr. Toma Cruz.
Hello. I'd just like to say na maganda po yung presentation niyo.
Thank
Yung
you.
question ko
Thank you
lang
po.
is, ano yung, what was your basis of measuring I think the greenhouse gas performance? Like, ano yung composition niya and saan niyo siya na source from? Thank you.
I think I would take this question. Thank you for that, Goran. So our basis actually for the GHG performance is from literature. So far, it has been a measure of the global warming potential of renewable energy technologies. However, we have found just a few days ago that there are actually 17 other midpoint indicators of environmental impact and endpoint indicators of environmental impact under the recipe method, which we will be looking into more as we progress in the methodology.
Okay. I would like to ask a question pero wala nang time. Sige. Thank you so much, Miss Suebagio and Miss Passion for that.
Wala, nag-freeze si 30. Everyone, sorry for the technical difficulty. Let's wait for Dr. Tomolva to re-enter the meeting. Okay, so again, thank you to Ms. Passion and Ms. Suwaybagi for that presentation. Okay, so we now go to our fourth presenters. We have Ms. Calderon, Ms. Eusebio, and Ms. Villar under JMA4.
Ayan, sorry.
Welcome back, Sir T.
Well, thank you. It's good to be back. Okay, ay,
Or may pahabol ka ba, sir?
Hindi, wala naman. Sige, let's proceed to the fourth group na.
Good morning. We are Cristiana Calderon, Jana Eusebio, and Katrina Villar from the Spark Laboratory. Under the supervision of our laboratory head, Dr. Jude Aberelia, we will be conducting a study to quantify the environmental sustainability of virgin coconut oil production in the Philippines. Coconut is one of the major agricultural products in the Philippines. It is well known that the Philippines is the second largest coconut producer in the world, with 68 out of 81 provinces being coconut producing. In 2019, the Philippines was able to produce 14.8 million tons of the 62.9 million tons of coconut produced globally. A few notable coconut products include virgin coconut oil, coconut water, coconut flour, and coconut meal. Because of globalization, agriculture has been continually expanding its operation and production. In this process, the resources it has consumed have compounded to 70% of global freshwater use and 37% of global land area. It is also responsible for 24% of global greenhouse emissions. Coconut production contributes to agriculture's environmental burden as it consumes huge volumes of water, land, and fertilizer. Its cultivation also results in soil nutrient deficiency because the coconut is a monocrop. Due to agriculture's environmental impact, there is a need to consider the sustainability of this sector. This is in conjunction with the 12th SDG, which calls for responsible consumption and production. A sustainability assessment can help achieve this. Additionally, it can help determine areas in coconut production that can be optimized, which is the main focus of some of the projects spearheaded by the Department of Agriculture and the Philippine Coconut Authority. For our study, we'll be focusing on assessing the sustainability of the virgin coconut oil production. The Philippines is one of the biggest exporters of virgin coconut oil. Virgin coconut oil, commonly known as DCO, is a type of oil extracted from the coconut kernel. No heat is used after extraction, and processes such as chemical refining, bleaching, and deodorizing are not utilized, leading to the preservation of the oil's natural properties. Some applications of VCO include health applications and non-health applications like body lotion and soap.
From the processing manual for virgin coconut oil of Dr. Divina Bawalan, the processing technologies in the Philippines include the following. VCO processing technologies can be categorized into two types. These are the processes under fresh-dry processes, and these are the processes categorized as fresh-wet processes. Fresh-dry processes make VCO from fresh coconut kernels, which are dried before oil extraction is done. There are 5 processes classified as such: high-pressure oil extraction methods with its 3 routes, low-pressure oil extraction method, and the fresh-dry centrifuge method. Their byproducts include coconut flakes, coconut meal, and coconut slurry and wet testa respectively. Fresh wet processes make use of coconut milk or coconut milk residue extracted from fresh coconut kernels to produce VCO. These processes create the following byproducts. For the centrifuge method, coconut skim milk and coconut milk residue are produced. The modified kitchen method produces coconut skim milk and coagulated protein, while the fermentation method produces curd and fermented coconut skim milk. The Bawalan Masa process, which is a combination of wet and dry processes, produce coconut flakes. Among the literature we have reviewed, we found a lack in studies conducting a sustainability assessment of VCO production. Despite discussing the process, the literature did not address the aspect of environmental sustainability and did not account for energy consumed and waste produced in the operations. This notable gap in the literature motivated our team towards conducting a study revolving around the sustainability assessment of VCO production. Not only will our study be able to provide essential insight on how to further develop and optimize VCO production, but we believe that these insights in sustainability would be able to contribute to an increased profitability for the production.
This study aims to quantify the environmental sustainability of different manufacturing processes of virgin coconut oil production in the Philippines. Specifically, the objectives are to measure material and energy inputs such as coconut input, solid waste product, wastewater, and energy consumption of each process, to conduct a life cycle assessment and use sustainability indicators to assess the sustainability of the processes, and to compare the sustainability of different manufacturing technologies of virgin coconut oil production in the Philippines. Notable areas for improvement will be determined by sustainability factors so that our goal of a more sustainable coconut industry can be fulfilled. Following the 4 stages of life cycle analysis, our methodology is further expanded into 5 phases, namely goals and scope definition, data gathering, inventory analysis, impact assessment, and interpretation. Our study will follow an attributional modeling approach with a gate-to-gate life cycle system, Boundary focusing solely on the production stage in the life cycle of VCO. A non-assertive comparative LCA study application approach will be utilized with one letter of VCO as a functional unit. For data gathering, primary data will be collected through interviews and coordinations with VCO producing companies, organizations, and the Philippine Coconut Authority. The nature of primary data to be collected include material inputs and outputs, overall performance of production, standard properties of raw material, and annual environmental reports. Secondary data will be obtained from established databases such as EcoInvent, Agribilis, and the like. For example, for the grated coconut root, under the high expeller extraction fresh-dry process, data regarding the material inputs and outputs from the operations involved, such as the amount of coconut fed to dehusking, coconut water from splitting, coconut flakes after expelling, and the like, will be obtained from the Philippine Coconut Authority and VCO producing companies that use this route. The collected data will then be subjected to material flow and energy analysis in every stage of the process. Process simulation through the use of SuperPro will be used to fill in gaps in data that cannot be obtained from primary and secondary sources. After performing material and energy balances as well as process simulation, the next steps in data processing involved impact assessment and interpretation of results. The study will be using Recipe 2016 model of analysis following its 17 midpoint impact categories, which include water use, global warming, and human toxicity. The obtained impact scores for different VCO processing technologies will then be compared to determine the areas that need optimization. Through this study, we hope to be able to further the initiatives towards a more sustainable virgin coconut oil production in the country. Thank you very much for your time.
Okay, thank you very much to the last group. Ayan, merong agad nakabang na tanong from Miss Passion. Sige, Miss Passion, what's your question for JMA4?
Hello po. I just wanted to ask po, how were they able to identify the technologies that they were going to evaluate, like the fresh wet and fresh dry technologies?
Hello po. Ayun. I'd like to answer this question. We originally found 3 handbooks. One was created for the National Academy of Science and Technology, one by Bawalan and Chapman in 2006, and one by Bawalan in 2011. The reason why we chose Bawalan's manual in 2011 is because it is the latest version, and additionally, because the Bawalan that wrote the book was the creator of the Bawalan Masak process, which is one of the processes that we will be analyzing. Additionally, the manual was recommended to us by the Philippine Coconut Authority's Research Development Branch.
Okay, are there any more questions? Okay, I just want to ask something. Why did you choose to focus this sustainability study on the production of specifically virgin coconut oil? Like, anong meron?
I'd like to answer that question. Like we have searched literature po, and we've discussed na virgin coconut oil has a wide variety of applications such as food and medicine na rin po. But we noticed that among those literature, walang nagfo-focus on the sustainability of the product itself. So considering that it's something that's widely used and distributed, we thought that it should be that a sustainability study on its process would be conducted?
I would also like to add to that. We mentioned earlier that the Philippines is the second largest producer of coconuts in the world. So, and aside from that, we are also the largest producer of coconut oil and virgin coconut oil. So, because of that, if we were to conduct a study on production in the Philippines, that could extend to a global scale because we are one of the largest producers of the product.
So you feel like it's imperative that there's a sustainability study for such particular industry because the Philippines is such a major key player in the global market of virgin coconut oil. Is that what you're saying?
Yes po, and we believe that it will help the VCO industry because Philcoa itself said that in an article published by Philcoa, they said that VCO has a high potential to be a marketable product. So we believe that this environmental sustainability assessment can really help us determine which areas can be optimized so that it can increase the profitability of the production.
Okay, thank you very much for that answer. Okay, so thank you for that presentation, Miss Calderon, Miss Eusebio, and Miss Villar. Okay, so now we're done with the groups from uh, the laboratory of Dr. Jude Averilla. Now let's proceed to the two groups under the advisement of Dr. Joey Ocon. Let's start with the first one, GDO1, and the group is composed of Mr. Jonas Angelo Abadilla, Miss Larissa Lim, and Mr. Felix Andre. And the title of their thesis is Battery Capacity Estimation Using Data-Driven Machine Learning. Okay. So the group GDO1, you have the floor. Please proceed.
Good day, everyone. I am Jonas Angelo Abadilla, and together with Larissa Lim and Andre Felix Tan, we are GDO1, and we will be presenting our proposal for our research topic entitled Battery Capacity Estimation Using Data-Driven Machine Learning. For the outline of our presentation, we have the introduction, the specific and general objectives of the study, the proposed methodologies, future work and work plan, and timetable for the next semester.
First, let's talk about lithium-ion batteries. The continuous rise in population, industrial development, and economic growth has tremendously increased the demand for energy. With the depletion of fossil fuel and the magnification of its detrimental environmental effects, the need for renewable energy arises. In this shift towards adapting a renewable energy-based power generation, the use of battery energy storage systems such as lithium-ion batteries have proven itself with its technology and potential. Lithium-ion batteries offer a variety of chemistries, each with its own set of advantages. In general, the defining features of lithium-ion batteries are its high energy and power density, high single-cell voltage, high energy efficiency, and low cost. However, lithium-ion batteries experience capacity fade over time and use, thus affecting performance and lifetime. The schematic illustration of charge and discharge processes are shown in Figure 1. The two primary causes of capacity degradation have been identified to be the loss of lithium inventory, or LLI, and the loss of active material, or LAM. Underlying LLI are the solid electrolyte interface formation and lithium plating, among others, while LAM is caused by the loss of electrical contact, particle cracking, or structural disordering. These are illustrated in Figure 2. Because of the complex interplay of the physical and chemical processes, the establishment of battery degradation mechanisms remain as the most challenging goal in the battery industry. In the improvement of managing battery energy storage systems, estimating battery capacity is then vital, as battery capacity is a key indicator of the overall battery performance and cycling life.
There are several approaches found in literature that estimate the state of health of the battery and then relate it to its capacity. Experimental methods, such as the electrochemical impedance spectroscopy and incremental capacity and differential voltage analysis, are some of the more common approaches for capacity estimation. They can be used for different lithium-ion cell chemistries. However, these methods require extensive experimentation and are sensitive to measurement noise, thus requiring a lot more computational power, making them unsuitable for real-time capacity estimation. Model-based methods, such as the equivalent circuit model, the electrochemical model, and adaptive filters, are also common approaches for capacity estimation. These methods produce highly accurate estimates, but their accuracy is dependent on the choice of the battery model. Additional challenges for these methods are the identification of the model parameters to account for the underlying cell degradation mechanisms, and the presence of many partial differential equations, which would require higher computational power. These limitations are overcome by using data-driven machine learning methods, which are gaining much attention from battery researchers and have shown great potential for battery capacity estimation due to the advanced capabilities of machine learning algorithms. An advantage of this method is that it requires no prior knowledge of the battery chemistry and requires no existing battery models to make predictions and estimations, as it can build analytical models by itself. One drawback, however, is that it relies on the quantity and the quality of training data to achieve an accurate prediction. Data analysis through machine learning is based on the idea that a computer can learn from the data, identify patterns, and make predictions with minimal human interaction. The general workflow for machine learning begins with the measurable parameters recorded by the battery management system during cycling, such as the current, voltage, and temperature. These data are filtered, and the parameters leading to cell aging are extracted. These are then used to train the machine learning model, after which the model will be used online to predict or estimate the remaining useful life or state of health of the battery. Machine learning algorithms are classified into two. The non-probabilistic approach. Outputs are obtained through a known relationship among the different parameters without necessarily considering its probability distributions. Common estimation algorithms under this classification are the artificial neural network and support vector machines. In the probabilistic approach, the level of uncertainty for each estimate is given alongside the output. Some examples include the random forest regression and the Gaussian process regression.
The general objective of the study is to compare the performance of machine learning methods in the estimation of battery capacity. The specific objectives include replication of the data-driven machine learning method from Richardson, to analyze other available datasets for battery capacity estimation, and to evaluate other data-driven machine learning methods through neural network SVM and random forest. This is the proposed methodology. In this proposed research, we want to estimate battery capacity using data-driven machine learning methods. Likewise, we want to compare the accuracy of these methods on the datasets that we'll be using. This will be done by employment of these methodologies.
The first step is to replicate Richardson et al.'s method. They use GPIs, or Gaussian process for in situ capacity estimation, to estimate capacity using the Oxford and NASA datasets. Our group will be using GPR, or Gaussian process regression, to model the Oxford dataset. Figure 4 shows an overview of the data used by Richardson's team after pre-treatment. This final data is expected to be the galvanostatic voltage curve, or simply the voltage versus time curve. The models produced by our team will be compared with those obtained by Richardson's team via RMSPE, or root mean square percentage error, as an evaluation tool.
Next, other datasets for battery capacity estimation will be analyzed. Some considerations are the feasibility of processing and the extensiveness of the data. Possible datasets are those from NASA, HNEI, and CalCi. Shown in Figure 5a is a snippet of the Oxford dataset. The model developed from previous step will also be used on the chosen dataset. Lastly, other data-driven machine learning methods will be used on the chosen datasets. The performance of these machine learning methods on the chosen datasets will be verified and compared to see which machine learning method produces the most accurate estimate for each dataset. Overall, we are aiming to compare the performance of at least two machine learning methods on at least two datasets.
In conclusion, our study is important because capacity is a vital indicator of a battery's overall performance and efficiency. Our work can be used in future studies as estimated capacity can be correlated with lifetime predictions. Our work can also contribute to the current understanding of battery degradation mechanisms. Prospects for this line of work include building better models that have high accuracy and wide applicability, and learning machine learning models with experimental and model-based methods as these were studied to build models with better performance.
For the work plan and timetable for the next semester, we have the following. First, for the first month, we will be replicating the Richardson method from using the Oxford dataset. For the second month, we will be evaluating replicated model on other datasets. For another additional 2 months, we'll be training and verifying other data-driven machine learning methods on the chosen datasets. For the last 2 months of the semester, we'll be finalizing our thesis writing for the written manuscript and the final defense. That's all for our presentation. If you have any questions, feel free to send us an email to our contact details on the screen. Thank you very much for listening.
Okay, thank you very much to the group of JDO1. Are there any questions from the audience?
Hello.
Yes, Mr. Rao.
I have a question. Like, how do you propose to partition which is the training set and the test data set? Like, how would you partition it? Like, would they be within the same data set? Like, for example, both the training and both the test and the training are in the same data set, or will you have this cross data set, like training from this data set, but the test would be on a different data set? So how would you partition it, or like just any plans? Like, how would you partition those?
For the Oxford dataset, we plan to use only the Oxford dataset for training and testing, and we plan to partition it maybe a certain percentage of the dataset will be used for training, and then a certain percentage will be used for validation and testing. And then the model will also be used in other datasets so that we can also test its scalability. And that's what we plan to do.
Okay, thank you.
A follow-up question, why 30%?
It's initial plans. It is our initial plans. So we will be we'll be trying to actually check kung ilang percentage po yung gagamitin namin for testing and
Okay, so you will also investigate the sensitivity of this partitioning. Okay, sige. Are there any more questions from the audience? Actually, I have the same question na tanong na. Siguro I will just leave one comment on your, I think it was slide 5, comparing the 3 different approaches, no? You gave the pros and cons, but in order to sell your choice of doing machine learning, I think it would be better if you just tabulate all the criteria, the entire set, and then you try to evaluate all 3 methods. Kasi I noticed hindi sila aligned yung mga advantages, the pros and cons with each other. So I have no idea, parang we will not have any idea how much will be sacrificed if you choose one option over the other. Okay, parang yung isa mas accurate pero yung isa mas has a different has a different advantage. Okay, pero there's nothing in the list that says what about the accuracy? Kasi yung isa is accurate, how about the other one? Is the accuracy severely compromised or hindi? So yun lang. So yung list lang na yun, maybe in your final manuscript, ano lang, just to be able to rationalize the choice of machine learning. Okay? So yun lang yung contribution ko sa study niyo. Admittedly, I'm not an expert in machine learning. Okay. Okay, so if there are no more questions, that's it for JDO1. Thank you so much for that very nice presentation. And now we will move on to the final group of presenters for this session number 2. And it's still under the advisement of Dr. Joey Ocon. Okay, so the group is composed of Mr. Hezekiah Antonano, Mr. J. Mark Panganiban, and Mr. John Vincent Yu. And the title of their thesis proposal is Multi-Physics Modeling of High-Temperature Planar and Tubular Sodium-Sulfur Batteries. Okay, so the group JDO2, you now have the floor.
Good day, everyone. I am Hezekiah Antonano, and along with my research group mates, J. Mark Panganiban and John Vincent Yu, we are Research Unit JDO2. Today, we are going to present our research proposal, which is called the Multi-Physics Modeling of High-Temperature Planar and Tubular Sodium-Sulfur Batteries. Today, this is the overview of our presentation. We will begin with the introduction, then explain the objectives along with the methodology, and lastly, we will present our timeline. Energy storage systems are an integral part of any electrical grid. Excess electricity can be stored when the supply is greater than the demand, and then released when the demand exceeds supply. This can help stabilize the grid, counteract electrical interruptions, as well as have applications in renewable energy. One of the rising energy storage technologies are sodium-sulfur batteries, which have low cost, high efficiency, high energy density, and long shelf life. And now, we will discuss the chemistry of sodium-sulfur batteries. Sodium acts as the anode, while sulfur acts as the cathode, and the beta-alumina solid electrolyte acts as the electrolyte. The beta-alumina solid electrolyte is also called as base. For the discharge cycle, sodium donates an electron to the external circuit. Sodium ions then pass through the electrolyte to the positive electrode and form a sodium polysulfide. For the charging cycle, you can follow the blue arrows in the diagram. First, sodium polysulfide decomposes and sodium ions migrate back through the electrolyte. Sodium-sulfur batteries come in two geometries, tubular cells and planar cells. Tubular cells have the advantages of ease in increasing cell size and have higher mechanical stability at its base. Planar cells, on the other hand, have an ease when it comes to stacking, have better thermal dissipation, which results in better power output, but unfortunately, it has sealing and mechanical stability issues with the base. As a result, tubular cells are the more dominant in the market in these past few decades.
A multi-physics model is a mathematical model which incorporates various physical phenomena such as heat transfer, mass transfer, charge transfer, and others. It is useful for describing systems where the properties of the entities in the system are coupled to other variables. This may be used to model devices such as batteries to be able to provide a comprehensive, high-accuracy description of the device's operation. It can consider material properties, battery chemistry, and cell-level design parameters to achieve high predictive power with minimal experiments. These models can simulate various designs, which can be analyzed and optimized by adjusting parameters and specifications in the calculations. An example of an application of multi-physics modeling includes studying of temperature distribution in a system, which allows us to design safety measures to prevent thermal runaway. In recent years, there have been a few multi-physics models developed for the study of tubular sodium-sulfur batteries. In 2016, Mason published a highly comprehensive multiphysics model of a tubular cell incorporating charge conservation, mass conservation, and heat conservation to study the effect of capillary pressure. In the same year, Eigel developed a fast and robust computational model which involved the use of a 3D thermal model for thermal management of a single cell and a cell configuration for use as an energy storage system. In a 2020 study on transition modeling for sodium-sulfur batteries by Schaefer and others, each of the major components, the sulfur and sodium electrodes, and the base electrolytes, were provided with a set of transport equations. Although there have been a few multiphysics models developed for tubular high-temperature sodium-sulfur cells, we found a lack of studies and models concerning planar ones.
Our main goal will be to develop tubular and planar multiphysics models for the high-temperature sodium-sulfur battery in order to compare the two geometries. In particular, we will use COMSOL multiphysics to replicate a previously established multiphysics model that was developed by Schaefer et al. For the tubular geometry. Schaefer et al.'s work provided experimental data which will be used to validate the accuracy of the model developed in COMSOL. Afterwards, the model will be modified to develop a multiphysics model for the planar geometry. The planar geometry will be based on the dimensions of the planar cell in the work of Kim et al. The model's accuracy will then be validated using experimental data from the same work. The two geometries will be compared using various parameters. The multiphysics model developed by Schaefer et al. Was selected for replication in COMSOL since it was able to model all three major components of the sodium-sulfur cell, as well as provide a complete set of model parameters. In COMSOL, we will use physics interfaces such as heat transfer, mass transport, and current distribution interfaces to replicate Schaefer's model. We will then compare our model results for the temperature profile and the discharge profile with those in Schaefer's work to determine the validity of our model. We will perform qualitative comparison with the experimental data to be able to locate possible sources of deviation. The following table describes the multiphysics model developed by Schaefer et al. The heat transfer in each of the components is transient and unidimensional. All components experience ohmic heating, while the sulfur electrode will additionally experience heat transfer due to the chemical reaction. For the sulfur electrode and the base, the ionic current is a consequence of the ionic potential gradient and the sodium ion concentration gradient. Meanwhile, the base is electronically insulated, and electronic current through the sulfur electrode is a consequence of the electronic potential gradient. The charge conservation in the sulfur electrode is additionally affected by the reaction over potential. The sodium ion conservation for the sulfur electrode is determined based on the exchange current density, which can be related to the reaction over potential. The sodium ion conservation in the base is derived from porous media diffusion. The sodium ion conservation in the sodium electrode is based on the volume of the electrode and the total current. The sodium ion also has an ionic potential drop equal to the overpotential obtained through the Butler-Volmer kinetics. The boundary conditions established by Schaefer et al. For these differential equations are given in cylindrical coordinates, but we will be modifying these to rectangular coordinates for our planar model. Using the modified boundary conditions, we will develop the multiphysics model for the planar high-temperature sodium-sulfur battery. We will be using the cell dimensions provided in the study of Kim et al. To develop the model. We will then compare our model results for the discharge profile and for the derivative of voltage with respect to the depth of discharge to the experimental data from the work of Kim et al. We will again perform a qualitative comparison with experimental plots to be able to determine the possible sources of deviation. Lastly, we will compare the two geometries using the following parameters: voltage, energy density, power density, and the maximum operating temperature. Finally, this is our work plan and timetable. We intend to finish our work in 6 months. For the first 2 months, we plan to use our time to improve our skills in COMSOL multiphysics, replicate Schaefer et al.'s multiphysics model for the tubular geometry, and verify the accuracy of the developed tubular model. Then, we will spend the next 2 months developing our planar model based off the previously established tubular model. Lastly, we will spend the remaining time writing our manuscript, and preparing for the defense of our thesis. This is the end of our proposal. Thank you for listening.
Okay, thank you very much, JDO2. The floor is now open for questions from the audience. Are there any questions from the audience? Wala, gutom na. Ay. Okay, again, can you just enumerate, kasi you're doing transport studies, and I'm interested to know what are the assumptions that you're going to impose when you're doing your transport modeling effectively, diba?
Okay. So the things like the boundary conditions in particular.
Yes.
Okay.
And if you're going to impose any other simplifying assumptions.
Actually, our plan is to replicate the assumptions and some of the boundary conditions from the work of Schaefer et al. Then afterwards, we're going to try to apply that to a planar model by changing the boundary conditions to make it for a planar system.
And when you say replicate, so that's inherently an assumption, right? That your system has the same boundary conditions as that of the one previously done.
Yes.
Okay. Okay. Sige. Wait, teka lang. Modeling kayo, no? There will be no experimentation, right?
Yeah, there will be no experimentation.
Walang metla. Okay. Okay, so I guess if there are no questions from the audience, I think that's it. Thank you very much, JDO2, for that presentation. Okay, and that concludes all the presentations in this parallel session 2. Just a reminder, please return to the main colloquium meeting later this afternoon for some further announcements and for the closing remarks. Okay, and then before we log off, I just want to do two things first. First, let's do a photo op. So kindly turn on your video. Okay. How about Mr. Ong? Mr. Ong, can you hear us?
Hello. Wait lang po.
Okay. Yeah. Ganda ng background nung sorry, rinig pala. Yung sa sustainability lab. Very Animal Crossing. Okay. Ayan. Okay. So, Sir Mike? Sir Nico?
Okay po, sir. 1, 2, 3. Okay, one more time. 1, 2, 3. Okay po.
Okay, one more time. 1, 2, 3. Okay. And then, okay, so thank you very much. And then lastly, I just want to announce, kasi sabi, I was instructed to choose a best presentation. I don't know who to choose. I've narrowed it down to 2 groups. Pwede man dalawa, Sir Mike?
Isa lang daw, sabi ni Ma'am Jem eh.
What if one per lab naman eh? Pwede ba bato-topic na lang sila? Sige,
Pwede namang sir, co-best presenters. Call nyo naman yan as chair.
ito ba yun?
Hindi ko alam, sir. Invento ko lang yan.
Invento lang.
Or isa na lang para safe.
Sige. Sige. Sige, for this parallel session 2, the best presentation is from the group of Mr. Jonas Abadilla, Ms. Larissa Lim, and Mr. Andre Tan. Okay, so congratulations. You will receive you will be awarded your certificates later this afternoon. So, one of the reasons why you should go back to the main colloquium meeting. Okay, so that's it for this morning session, although lunch break na. Sige, thank you very much for attending, and we'll see you all back later this afternoon for the closing remarks. Okay?
So just a reminder din po, this meeting link will remain open and so until the end of the second session this afternoon. So open lang tong link, open lang din yung live stream until the start of the next parallel session. Okay, so feel free to join any other parallel session next this afternoon. So congratulations for defending your proposals today. And yeah. Okay, that's it.
Okay? Sige. Session adjourned. Sir Mike, ikaw ang host.
Okay. Yes, sir. Okay na.
Close mo na.
Hello, good afternoon, everyone. We will start in a few minutes. Hello, good afternoon, everyone. Rinig ba ako? Ayan.
Good afternoon, sir.
Good afternoon, guys. Okay, so welcome everyone to Parallel Session 7. Welcome to this afternoon's session for the Chemical Engineering Undergraduate Research Colloquium. And this time, you will now have your CHE 144 final thesis defense. So congratulations to everyone to making it this far. Konti na lang and patapos na. Okay, so for Parallel Session 7, I will be your host. We have Dr. Ram Tamargo as our panel chair, and we have soon to be Dr. Isaac de la Cruz to be our panel assistant. Okay, so lang. So this for today, this session, we will have 2 groups under the FETS lab and 3 groups under the Spark lab. Okay, so before anything else, house rules. Yep. Ayan. So for our house rules, so again, please take note of the following. So please mute your microphones and please turn off your cameras while the presentations are ongoing. Your uploaded YouTube videos will be presented or will be played by the host during your time slot. So I think that's 15 minutes, followed by a 10-minute Q&A forum. So to ask questions, please use the meeting's chat box, and this will be read out by the panel chair. For any questions you want to ask to the presenters, just please raise your hand during the Q&A and wait for us to acknowledge you before unmuting. Yan. And then again, this session is being live streamed and recorded, so live stream to via YouTube, so we will appreciate your proper behavior. So that's it for the house rules. And siguro for each presenter, I will be making you co-host during your Q&A in case you need to share your PowerPoint slides presentation, in case you prepared additional slides or additional material for your Q&A. All right, so please pakiready na rin nung mga additional materials just in case. So without further ado, I now turn over to the panel chair.
Hello. Good afternoon, everyone. Welcome to parallel session 7. So we have here two thesis defense under FETS Lab and Spark. The first group will be under FETS Lab, and their advisors are Dr. Rizzalinda De Leon and Engineer Christian Jolaya. The title of their thesis is Evaluation of an Ion Exchange Membrane, Functional Groups, and Investigation of Temperature Effects on an Ion Exchange Membrane, Water Electrolyzer Performance for Hydrogen Production. Let's all welcome Ms. Depana and Ms. Escota.
Good day, everyone. I am Avril Joel A. Escoto. Together with me is Kirsty Alisame and Dupano. We are one of the undergraduate researcher pairs from UP Fuels Energy and Thermal Systems Laboratory under our advisors, Dr. Isalinda De Leon and Engineer Christian Julaya. We are here to present our undergraduate research entitled Evaluation of an Ion Exchange Membrane, Functional Groups and Investigation of Temperature Effects on an ion exchange membrane water electrolyzer performance for hydrogen production. Here is the outline of our research presentation. So let's start with the introduction. Hydrogen, as an abundant substance in the universe, can be produced by various methods such as thermal, electrolytic, and photolytic processes from fossil fuels, biomass, and water. Currently, about 85% of the overall energy consumption worldwide is obtained from non-renewable sources, which contribute to the environmental, economic, and political issues. These resources are finite and are currently depleting. So, in order to mitigate the effects of climate change and attain sustainable development, we need to drive the shift towards the use of a clean, renewable, and economical fuel. Hydrogen is considered as an ideal storage medium, converting energy from renewable power sources into chemical bonds with a high energy density. So through renewable energy, we can produce hydrogen by electrolyzing water, store it, and use it to generate electricity through fuel cells. Indeed, renewable hydrogen promises an alternative energy carrier to generate power, as well as reduce carbon dioxide and greenhouse gas emissions, and mostly to become independent from fossil fuels. The current solution is through water electrolysis, which is a well-developed technology for the conversion of water into hydrogen and oxygen at low temperatures. Some established technologies of water electrolysis are the alkaline electrolysis, proton exchange membrane electrolysis, and solid oxide electrolysis. In this study, we focus on an ion exchange membrane water electrolysis. One of the major advantages of AEM water electrolysis is it is low cost, it produces high purity hydrogen, and has compact and efficient system design. However, AEMWE is still a developing technology and thus subject to further investigation and improvement. AEM, as the chief component, determines the performance of a water electrolyzer. The main parts are the polymer backbone coupled with an ion exchange functional group. Ideally, AEM should possess adequate chemical stability, high hydroxide conductivity, good thermal stability, sufficient mechanical stability, and excellent long-term durability. The highlighted characteristics have been considered as the most important properties for use in practical systems, and this can be improved by choosing the suitable functional group. Functional groups are accountable for ion exchange capacity, ionic conductivity, and transport number. It is responsible for the transport of hydroxide anion while minimizing the amount of hydrophobic bulk. Shown here are the common chemical structures of AM functional groups. So far, there is no consensus on the best AM as each functional group has its strengths and weaknesses. In an ideal situation, the best AEM head group is one that is both functional and practical. For this study, we are limited to three functional groups such as the imidazolium, piperidinium, and quaternary ammonium. This slide presents the degradation pathway of the functional group after exposure to alkaline environments, since the hydroxide attack may reduce the conductivity of the membrane.
In our research on the current state of AEM water electrolysis studies, we have identified a few problems or gaps in available research. The first problem found is that the current mathematical models to describe AEM water electrolysis are lacking. The second problem identified is the poor chemical stability of AEMs, which is one of the most important properties in practical systems. To improve chemical stability, the polymer backbone and the functional group must be identified for various properties such as ion exchange capacity and ionic conductivity. Lastly, the cost of hydrogen production is rarely noted alongside the studies of AEM water electrolysis. However, it is important to note these, especially in considering operating conditions, since the bulk of the hydrogen production costs are from the power supply. To address these research we propose to conduct our research with the general objective being design an anion exchange membrane water electrolyzer or AEMWE for hydrogen production. And the specific objectives are to evaluate membrane properties and stabilities of AEM with various functional groups, to predict the performance and efficiency of each membrane based on its ionic conductivity in AEMWE at operating temperatures 293.15 and 353.15 Kelvin. And finally, to recommend a suitable functional group that will improve the overall performance and efficiency of AEMWE for hydrogen production. Our study addresses the gaps identified earlier, improves understanding of the system taking a step towards commercialization, and adds to the development of technologies that provide clean and affordable energy. This study, however, focuses on the performance of functional groups in a one-dimensional membrane electrode assembly simulation. The data and mathematical models used are from accessible published data. To accomplish our objectives, we followed this methodology, which is divided into 4 parts: data gathering, membrane properties evaluation, AEMWE simulation in varying temperatures, and simulating the various membranes in the set conditions. Microsoft Excel was used for part 2, while MATLAB was used for parts 3 and 4.
As stated in the study's limitations, data will be collected from available journals and will be evaluated through simulations. Hence, the following must be gathered and supplied to the analysis of this research: the membrane properties with its functional groups and polymer types, physicochemical properties of the anode and the cathode, operating condition parameters, structural properties of the membrane electrode assembly. In order to recommend a suitable functional group, the properties of the membrane must be evaluated and compared. The membrane properties also describe its membrane stability. IEC and membrane conductivity describes the chemical stability and ionic conductivity. The Young's modulus and tensile strength describes the mechanical stability. And lastly, the water uptake and swelling ratio describes the ionic conductivity and dimensional stability. In order to compare the membrane properties and the functional groups, qualitative and quantitative comparison will be done. The data will be normalized, then will be plotted in the radar charts to qualitatively derive comparisons. Lastly, the performance will be ranked quantitatively by calculating the area of the radar plot.
While data gathering and membrane evaluation was being done, simulation of AEMWE was being set up in MATLAB following the given models. First, mass transport of the gaseous species in the diffusion layer was set up, composed of the following equations. And based on the figure on the AEMWE to the right, the following boundary conditions are given, with liquid saturation being the same on interfaces 1 and 4, and oxygen and hydrogen evolution occurs at interfaces 2 and 3 respectively. Next, the electrochemical kinetics were modeled using Butler-Volmer equations on both electrodes. The voltage applied is then calculated adding the structural resistances, the activation potentials, and the Nernst potential. Finally, the Faradaic efficiency expressed in terms of voltage loss and applied is calculated. All these equations are then simulated in varying temperatures to investigate its effects on the AEMWE performance. Finally, for the last part of the methodology, the membrane data gathered is incorporated in the simulation. In this case, the ionic conductivity is incorporated since it is explicitly used in the mathematical models. Simulation then provides these kinds of outputs for each membrane at 293.15 Kelvin and 353.15 Kelvin.
I will now start the presentation and discussion of the research results. With all the gathered data, we have evaluated, characterized, and compared the membrane properties. Here is a radar chart of all the membranes discussed for this study. Qualitatively, the radar plot concludes that imidazolium has the highest mechanical stability and has good dimensional stability. Piperidinium has the best ionic conductivity, alkaline stability, and chemical stability. And lastly, quaternary ammonium exhibits poor stability and properties relative to the two functional groups. Here are the radar plots of membranes at specific functional groups. It shows here the individual performance of each membrane relative to its functional group classification.
On the side of AEMWE simulation, this slide shows a few of the generated plots. For this study, 5 types of plots were extracted and separated to compare the effect of operating temperature. The first plot shows the polarization curve, which relates the current density to the applied voltage. The second plot shows the efficiency of AEMWE. As seen on these plots, increasing the temperature improves the overall performance of the AEMWE, given that less voltage needs to be applied to accomplish the same production rate and increase in efficiency. This is further exhibited in the next plots, which show the losses, namely the ohmic loss and the overpotentials of anode and cathode. As seen from these graphs, the overpotentials contribute more voltage loss compared to the ohmic loss. As temperature increases, losses are lessened. In the final step, the ionic conductivity was varied in the simulation of the AEMWE to predict the performance of each membrane in the chosen operating temperatures. The first set shows the piperidinium functional group results. According to the membrane evaluation chart, PTP90, represented by the orange polygon, is expected to perform the best based on its properties. And this expectation was met when simulated as shown on the performance plots to the right, where PTP19 is represented by the red plot. This expectation, however, was not met in the next set of functional groups. In the case of quaternary ammonium, QAPESK107 is the most suitable according to the membrane evaluation chart, while 1018 is the best performing according to simulation. The same inconsistency can be seen in the imidazolium functional group results. This inconsistency occurred because the other membrane properties, although important, were not incorporated in the math model and thus were not accounted for in the AEMWE performance. However, looking at the overall ranking and scores of the membranes in evaluation chart and simulation, only piperidinium was consistent on all scores, and despite the rest being inconsistently ranked, piperidinium membranes were still deemed to be the most suitable for AEMWE simulations.
With all the presented results, we now come to the conclusion. Reviewing the specific research objectives, this study has successfully accomplished its goals since it has evaluated and characterized qualitatively through radar charts and quantitatively through area plot calculations the membrane properties and stabilities of AEM at various functional groups. It also predicted the performance and efficiency of each membrane through mathematical models and polarization curves. Lastly, this study concluded that the piperidinium is the suitable functional group which exhibited the best overall performance and efficiency of AEMWE. Hence, this study also attained its general objective to design an ion exchange membrane water electrolyzer for hydrogen production.
To further this study, we recommend the following: focusing on math models and simulation improvement, using software such as COMSOL, or adding more to the math model by incorporating the membrane properties, and further investigation on membrane functional groups, particularly piperidinium functional group, since it shows promising results in our study. And with that, my partner in line would like to thank you for listening, and we are now open to your questions.
All right. Thank you for the presentation. Does anybody in the audience or panel have a question? Kindly raise your hand or type in your question in the chat box. Yeah, panel?
Hi, sir.
Any question?
Clarification lang kasi hindi ko masyadong napansin if ano yung naging metrics nyo kung bakit sinabi nyo hindi consistent yung results nyo sa ibang membrane tapos consistent na siya kay Pepperidinium. Kasi hindi ko na napansin masyado sa slide. Kumbaga nag-trials ba kayo to determine yung consistency ng membrane? Or paano nyo nakuha?
To clarify lang po, sir, the question is the consistency of the results that we found. We compared the results of the radar charts and the simulations, and we ranked the performance of each functional group or membrane for both simulations, and only the piperidinium had consistent rankings while the others varied. For example, some of the quaternary ammonium membranes were ranked at 10, and then the other and its counterpart in the simulation would be ranked at around 8 or something else like that. So that's the summary. So there's an inconsistency with the rankings of the others.
Okay, I see. So, with regards to that, may idea ba kayo kung bakit hindi consistent yung sa ibang membrane?
Yes po. Based on our math models that we used po, the only membrane property that was used was the ionic conductivity, which is only 1 out of 6 of the membrane properties that we evaluated in the radar charts. So, and we did a more in-depth ranking process, ranking each property, just to make sure that that was the case. And true enough, the ionic conductivity was the one that was consistent with the ranking, with the simulations, and also just particularly the property.
Okay, so thank you.
Okay, anything else? Mayroon bang may question? I have a question. How did you rank the 3 functional groups in terms of chemical stability and alkaline stability?
Sorry, sir, can you repeat the question?
How did you rank the 3 functional groups in terms of alkaline stability and chemical stability? Meron kasi kayo nilagay doon, best in chemical stability, best in the alkaline. How did you rank it?
Actually,
did you use model?
No, sir. We only qualitatively compare the values and the parameters of the membrane. We come up to having piperidinium has the highest or has the best alkaline stability and chemical stability because based on literature, you can describe the stabilities, those 2 stabilities based on the ionic conductivity and the IEC and the swelling ratio. That's it. Just to add, the ionic conductivity affects also the water uptake and the mechanical properties and dimensional stability. So, giving importance to all the properties compared here in the radar chart is given consideration since they have interrelated properties.
So would you say that every time na merong kung alin yung may best ionic conductivity, they are also the best in terms of chemical stability and alkaline stability? Is that always the case?
It's not always the case, but for qualitative comparison, we translate having the best or having the highest ionic conductivity and ion exchange capacity. It has the best alkaline or chemical stability.
So based on the trends, but you showed earlier the degradation reaction of each functional groups, right?
Yes.
Have you tried checking the reaction rates or the kinetics of that degradation to say that piperidinium has the best chemical stability and alkaline stability?
we haven't looked into the kinetics or the the properties based on the chemical structures, but we have found out that the piperidinium has the best stability due to its chemical structures. But since the study is limited to the simulations, we do not have a way to incorporate that to our mathematical models. So we included in our recommendations to further study the piperidinium, focusing on the chemical structures and the kinetics and the like.
Okay, kasi you should be able to make it clear since you have also shown the degradation reaction, yung three reactions na ring opening, including the ring opening of imidazolium, piperidinium, right? So
Yes, yes.
nag-break up yung pinaka-molecule niya. So since you have shown that, I was assuming that you have also used that as your basis when telling or when ranking the stability of each functional groups. So you have better to make it clear than the study nyo, and hopefully also scope and then yung recommendations.
Alright.
Will do, po,
yes, sir. But just to add, we included in our slides the reason based on the chemical structure of the piperidinium. It has the piperidinium demonstrates high resistance against both the degradation pathway due to its chemical structures, of course. The presence of the heterocyclic quaternary ammonium makes the piperidinium exceedingly resistant against the alkaline degradation due to its steric shielding. So the geometric constraints of the structure of the piperidinium contributes to the increase in the transition state energy of those reactions.
Yeah, but imidazolium is also a cyclic and heterocyclic compound, right? I mean, it's hard to tell it this descriptively that it is stable based on those factors, where in fact other molecules also show similar, or they also falls under that same metric. So I mean, if lalo na nag-ranking kasi tayo like
okay.
So parang dapat merong numerical value that equates that kind of stability, but we don't have it, and thus we just base it on the how the literature describe each functional groups, right? So yun lang, kasi parang ano lang kasi yung iba meron kayong metric, meron kayong model, but on that case yun nga lang ginamit nyo yung pinaka-description. So para kasing medyo ano siya subjective kung wala kayong value. Yun lang naman.
Yes.
Yeah, any meron pa bang question sa audience? All right, if none, okay, we can go to the next presenter. The next group is their thesis title is Biomimetic Design Simulation on an Alkaline Water Electrolyzer Flow Field. So let's welcome Mr. De Los Santos and Ms. Sapio. All right, you may start.
Good day, everyone. I'm Joshua De Los Santos, and together with me is Shaina Jane Sapio. We are one of the groups under the Fuels, Energy, and Thermal Systems Laboratory under Chemical UP Diliman, Department of Chemical Engineering under Ma'am Rosalinda De Leon and Sir Christian Jelaya. We are here to present a thesis entitled Biomimetic Design Simulation on an Alkaline Water Electrolyzer Flow Field. Before we start, we just want to hope that everyone's safe and okay. Always stay healthy and hydrated since the weather is really unpredictable nowadays. Now, speaking of which, if you can notice, we actually either have a really hot, above normal temperature or really heavy rainfall recently. And what do you think causes this? What you're thinking is correct, global warming, something that is real and needs immediate solution. Now, the carbon footprint that causes most of the global warming emissions comes from fossil fuel plants. Because of this, alternative energy sources have been gaining popularity in recent years. A leading example of sustainable, renewable, and efficient energy conversion technology are fuel cells. Fuel cells are a type of energy storage mechanisms that convert chemical to electric energy. A lot of research has been done in optimizing fuel cells, specifically PEM or polymer electrolyte membrane fuel cells, because of their cheap and abundant energy sources. You would only need a continuous hydrogen and oxygen supply to keep the system running. But then we encounter another problem, which is the acquisition of hydrogen. As we all know, hydrogen is very difficult to store and obtain despite its abundance in the atmosphere. In order to solve this problem, the concept of AWE or alkaline water electrolysis has been explored. AWE is a chemical process that utilizes current to separate oxygen and hydrogen from water, which is the complete opposite of how fuel cells operate. There are two main types of electrolyzers, the PEM and AEM. In our proposals, we are focusing on AEM water electrolyzer because they have more benefits in PEM. As chemical engineers, we are focused on mass production, and one of the capacities of AEM water electrolysis is that it's able to produce hydrogen on an industrial scale. However, AEM and AWE is still very recent, so there are only a few amount of studies done in the matter. We were lucky since its counterpart, the PEM AWE, is something we can use as a basis for our parameter optimization. As you can see in the slides, the AEM and PEM consist of the same structure and parts. They only differ on what type of ion passes through the membrane. The AWE is composed of the anode, cathode, and AEM, which is collectively known as the MEA. Now, the bipolar plates are the one responsible in keeping these components intact. They are like the glue that keeps the pieces together. Other than that, they are also responsible for the distribution and transport of ions during the process of electrolysis. They are the pathways through which the reactants and products pass through, so it's considered to be one of the most important parts of the electrolyzer because without it, there would be no fluid flow. Now, in order to have an efficient hydrogen production, the bipolar plate configuration must be optimized. There have been a lot of bipolar plate design variations throughout the year, and each design has its own pros and cons. Listed on the slide are the conventional plate designs used by different companies and manufacturers. Now you may be asking, what variable should be our focus in order to optimize the production of hydrogen? Based on a review on related literature, we found out that uniform current distribution and water management are the two main factors that affect the device's efficiency. Uniform current distribution basically means that the current supplied into the plate should be distributed well to avoid hot and cold spots, which can cause damage to the device. Previous studies found out that among the conventional studies, only a serpentine design produced the desirable result. For water management, the same principle follows that the hydration should be lessened, and if not so, should at least be distributed well, because if this is not taken into consideration, flooding might occur, thus forming again the cold and hot spots.
The researchers aim to improve the performance of AWE serpentine bipolar plate design in terms of water management and current distribution by incorporating biomimetic design into the flow field channels. When we say biomimetic design, we mean adopting biological pathways and integrating them into our electrolyzers bipolar plates. Our specific objectives are to compare serpentine bipolar plate with biomimetic configuration bipolar plate in terms of their water management and current distribution. And lastly, to compare the effect of altering geometric parameters on biomimetic configuration bipolar plates. In order to achieve our objectives, first, we have to establish our assumptions, which is based on a study of simulating bipolar plate configurations of fuel cells done by Feng and Su. Also, the materials to be used are as listed below. All of these materials are derived from optimizations of previous studies. The operating conditions used in the study were derived from a research of Vincent and Besarabov in 2018, wherein they did simulations to obtain the optimal operating parameters for an AEM electrolyzer. Moreover, the dimensions and test conditions for the electrolyzer are based on the simulation done by Ferg and Su and can be seen as listed. For our biomimetic design, the xylem structure was used for bases. Shown in the slide is a side-by-side comparison of the xylem structure and our configuration. Meanwhile, to address the current distribution problem, the axon structure configuration was used. After finalizing the assumptions, equations, and parameters, the modeling process to simulate fluid flow dynamics in the bipolar plate by Feng and Su is used. The simulation was done using COMSOL Multiphysics 5.6 CFD and electrochemistry modules. The complexities of a biomimetic bipolar plate could lead to difficulties in the design, since biological pathways could be too complicated and difficult to replicate in the COMSOL multiphysics that is used for the study simulation. Also, the hardware specifications available is Lenovo IdeaPad Slim 3 8GB RAM, Intel Core 1.710 Gen with 1.8 GHz processor using one socket with 4 cores in total. This is the most advanced and fastest computer that the researchers have access to during the pandemic, so some simulations take longer than others. The data set gathered from these simulations will be presented in the following slides to address the water management and current distribution problems faced by AWE electrolyzers. Shown in the figure is the serpentine design built in using the AutoCAD function of COMSOL 5.6. The stagnant areas in the serpentine design were shown in the figure, wherein the blue spots along the turn signify a velocity of 0 meters per second. Moreover, a pressure drop of 10.539 Pascal was observed across the serpentine flow field with uniform pressure gradient throughout the surface. The xylem structure was the key concept for the chosen biomimetic design. Slits were provided to allow water to flow through parallel vessels. The slits were set to a thickness of 0.03 mm, which was the highest size for a xylem cell conduit diameter, according to Comstock and Sperry. Compared to the serpentine design, the biomimetic design has a lower pressure drop of 10.421 Pascal, which is lowered by 1.12% that of the serpentine design. To further probe on the pressure values across the BPP, a 3D cut line was done along the center of the XZ plane, and to show the gradual effects of conduits, the pressure profiles of a serpentine design with increasing number of slits were shown in the figure. The pressure drops of all structures decrease as the number of slits increases. Comparing the pressure values upon entering and exiting the plate, the figure shows that for all structures, the difference in pressure values only happen near the inlet and converges in zero as they approach the outlet. This happened due to the no backflow boundary condition set by the researchers.
The following structure is used to simulate current flow in the biomimetic bipolar plate. In realistic setups, the anion exchange membrane is made up of composite material and catalyst, but for the sake of simplicity, the researchers decided to use a flat copper slab as the source of electricity. Due to the setup, the electricity is expected to flow from the origin coordinates towards the positive y direction. Incorporating slits affect the distribution of electric potential. Based on the simulation seen, the biomimetic design reduces the electrolyzer's tendency to have uneven concentration of electric potential. The serpentine design has a noisier plot compared to the biomimetic design. This means that the current is not distributed evenly in the plot that has noise in it. It can be observed that the slits produce an area of low electric potential. However, it seems like the electric potential difference relocated from the middle to the bipolar plate design turns. The figure shows a superimposed electric potential plots of serpentine and biomimetic. The biomimetic design has a relatively less noisy electric potential graph, which is consistent from the previous plot. A case study was done to find out the effect of difference in the width of the flow field. This configuration was done due to the second biomimetic structure, axon, that addresses the current distribution problem of a flow field. Based on its concept, a faster impulse reaction in animal is proportional to the increase in the width of the axon. Thus, the structure has a width of 0.5 mm is multiplied by 1.5 and 2 respectively. After the simulation, we found out that widening the fluid channel will affect the distribution of electric potential. The leftmost flows since there are almost no electric potential difference in the flow channel. As the width of the flow channel increases, the electric potential plot becomes noisy and uneven as seen in the other plots. The concentration of electric potential on the parts where water or fluid flows manifested again. This is not desirable since there will be energy sinks on various parts of the fluid path, which means that the current distribution is not as uniform as the ideal case. The figure shows a superimposed electric potential plot of the biomimetic design of increasing width. The biomimetic design still has a relatively least noisy electric potential graph, which is consistent from the previous plot. Only the biomimetic design of 0.5 mm has a relatively less noisy graph. The 0.75 mm channel has the noisiest electric potential plot among the three variations. This did not meet the expected results regarding having a more evenly distributed current flow as the flow channel width increases.
The same 3D plotline was done with the structures to probe on the pressure profile of the difference. In the figure, it is shown that as the number of slits increase, the pressure nearby the inlet decreases. This results to a lower pressure drop per additional number of slits. By increasing the width of the biomimetic structure, the pressure drop also decreases. The pressure drop in the 0.5 mm width structure is at 10.4 to 1 Pascal, while 1.5 and 2.0 width have pressure drops of 4.346 Pascal and 2.413 Pascal, respectively.
The figure shows the effect of increasing number of slits on current distribution. Only the biomimetic design with 18 slits has a relatively less noisy electric potential graph. Overall, this case study proved that the biomimetic design provided the study favorable results and better values in terms of water management and current distribution than the typical serpentine design for AWEs. For our conclusion, for the water management, addition of conduits, reduced pressure drops, and no water accumulations in any area. Even with the varying width of flow field, the maximum velocity is still at 0.003 meters per second. For the current density, the biomimetic design reduces the electrolyzer's tendency to have an even concentration of electric potential, and it is much more evenly distributed using the biomimetic design. For the altering geometry, as the width of the biomimetic structure increases, the pressure drop decreases. And as the width of the flow channel increases, the electric potential plot becomes noisy and uneven. Due to the limitations and restrictions that the research group experiences, following recommendations are suggested for those who might be interested in studying bipolar plate flow field design. We recommend procuring a hardware that has specs good enough to solve both laminar and electric current module of COMSOL simultaneously. We also recommend scaling up the whole bipolar plate and retain the number of turns and fluid velocity from the original plate simulation. Another study would also be increasing the height of the slits and see how it will affect the current distribution. Also increasing the amount of voltage or current applied to the system since the researchers only utilize optimal values from related literature. If possible, we would also like to recommend simulating the whole alkaline water electrolyzer so that the overall effect of changing the bipolar plate configuration can be observed. That ends our presentation. Thank you again for listening. Again, I am Christian de los Santos, and together with China Jane Sapio, we are from the PETS Laboratory, and we are now open for questions.
Thank you for your presentation. So, meron bang may questions sa audience and panel?
Yes, sir, wala naman po.
Okay. So, you have mentioned that yung trend ng yung length ng width nyo with the difference dun sa potential and also the pressure drop, right? So, yes, so have you determined the sweet spot in terms of because you have shown only 3 samples, right? The biomimetic 1.5 and 2, right? But have you tried doing the model of parang kunin niyo yung pressure drop, yung equation of pressure drop and the length, yung width ng length? Yung size ng
Okay,
width.
sir. So, yes, sir. So, yeah, actually, sir, it's in one of our limitations since we can't simultaneously solve or simulate yung with the current density with the current distribution along with the pressure drop po. So, we just probe on the results separately po. So as you have seen po sa video, like hiwalay po yung simulation namin for the water management part and pressure drops and sa current density. Now for the ano naman po relation, we can relate po that that there is an improvement since what we did with the design is we improve the flow of the water, the fluid inside the bipolar plate, and it's it can be seen po na there's an improvement in terms of pressure drop and current density kasi po as we introduce slits into our design, the flow became more distributed, which nag-follow din po yung pagka-distribute din po ng current based on the theory.
Okay. So you assume dun sa potential, yung sa difference of potential, you just assume it na lahat sila walang pressure drop. Yun ba yan?
For the yes, opo, is yung what we did po is we set parang it's we freeze the simulation since we can't simulate the fluid na it's flowing po talaga. So what we did is we simulated the system, we enclosed the design, and then we introduced a current or electricity through the bipolar plate, and then we just observed po how the current was distributed throughout the design.
Okay, so what is the maximum allowable pressure drop in terms of this kind of design for AWE?
Shy.
For according to our research, sir, wala po siyang max na allowable pressure drop. Pero parang goal ng researchers right now is to lower the pressure drop since nagkakos nga siya ng mga spots which could damage the membranes.
Yeah, but your trend is you want it to be thinner as possible, but you want also it to be as wide as possible, right? Because you have two different factors. One is the pressure drop, and another is yung distribution ng potential nyo, di ba? So that's why I asked if you have determined the sweet spot between the two. Kasi if you know the maximum allowable pressure drop, so you can work with that kind of range to see kung ano yung widest possible slit na meron kayong minimum distribution variety, 'di ba? Yung discrepancy dun sa yung spread ng distribution nyo. So maganda kung meron kayong parang model lang na kahit model lang nung relating the two na equation of that pressure drop or yung size ng slit versus pressure drop, and then size ng slit versus the distribution. So parang meron kayong recommendation sa kanila kasi conflicting yung meron kayong ideal device, but your recommendation is parang kailangan nilang pumili sa dalawa but di ba? So paano sila pipili? So yung recommendation na pwedeng manggaling sa inyo, either meron kayong i-recommend na thickness so that parang compensated pa rin yung pressure drop, kasi if there's a pressure drop, you want to generate energy, diba? But if there's high pressure drop, it means you need more energy dun sa na-supply just to compensate for the pressure drop.
Yeah.
So parang para saan pa yung na-generate yung energy? Diba?
Correct.
So parang nag-consume kayo ng high energy just to make that device better. But the total energy that has been generated is not di ba? Parang hindi siya hindi it doesn't make sense. So dahil may mga, I mean normal naman talaga na may mga ganong klaseng design consideration. So maganda lang if meron kayong kind of sort of a model of na para lang dun sa mga gagamit ng AWE, and then lalo na kung ang factor of designing nila is yung size ng slit. Yan lang naman. So meron pa bang may question?
Sir, just to answer,
okay. Sige.
Just to add na lang din po siguro. Since the thesis is actually more focused on the geometric of phenomenon, like the biomimetic design and the phenomenon that it will bring into the bipolar plate design. So it's more focused on the physical lang po muna as of now, since we actually can't still come up with an equation for AWE, since ayun, it's a relatively new technology nga po, and ayun, there are really a few studies done on the subject. But we actually thought about incorporating these two parameters together, but then current distribution relies on a lot of factors din po. So I think it's we can also recommend exploring these factors such as the geometry, operating conditions, yung mga mass transport, and weighing them in terms of how it affects the bipolar plate. So maybe that can also be another recommendation to say.
Okay, yeah. Kasi I mean you don't need to have a general equation for the three factors, but lang, if makuha nyo lang yung, kasi parang ang nangyari yung minimum na biomimetic, yun na yung maganda. Diba? Baka it could be lower, or baka pwede pa nating lakihan ng konti. So,
Sir, may I add?
Yung siguro yung interval lang yung.
Sir, may I add? For the channel width po kasi, if larger yung width na measurement, possible yung cavitation. Lower yung nakikita sa trend na lower yung pressure drop as the width increases. Pero yung yung parang pwedeng magka-cavitation na magli-lead to damage din.
Yeah, merong naman ganong mga phenomena, and then but lang para mas solid lang yung recommendation nyo after checking this 3 slits, then para kasi yung original lang yung okay, ito yung maganda kasi maganda yung distribution niya, but baka pwede pa siyang bawasan or parang konting step lang makuha yung magandang, parang pwede mo pang lakihan yung original design nyo in such a way na okay pa rin yung ibang factor. Yun lang naman yung suggestion ko. And then if hindi na siya kayang i-implement, and then you can just put it into words dun sa recommendation, and then dun sa scope and limitations.
Got it, sir. Thank you po.
Thank you sa suggestion, sir.
Yeah, meron pa bang may question sa audience? Okay, if none, let's move on to the next batch of presenters under Spark. And their advisor is here, Dr. Jude Michael Aberilla. Okay, let's start with the first pair, Mr. Baginon and Salak. Their thesis title is Sustainability Assessment of Renewable Desalination in Remote Islands in the Philippines. Okay, you can start the presentation.
Good day, everyone. We're Arizelio Salak and Ralph Justin Baginon, and today we'll be presenting the findings of our CHE 144 thesis entitled The Sustainability Assessment of Renewable Desalination in Remote Islands in the Philippines.
Water is a limited resource, yet our population is ever growing. According to the data presented by Richie and Rosaire in 2017, the Philippine resource for natural renewable water source has been depleted up to 72% of its original capacity in 1962. If this trend continues, potable water would definitely be hard to source in the country by 2040. Concurrently, major disparity in global electrification has been prominent among rural areas. The growth rate of electrification and water delivery in the Philippines' rural communities are stagnant and lagging to the growth of its population. leaving almost 900,000 Filipinos without access to these prime necessities. SDG 6 and SDG 7 advocate for our basic rights to clean and affordable utilities such as water and electricity, respectively. In coherence with these goals, the introduction of renewable water and energy sources may be potential solutions to the country's looming resource scarcity. The geographical location of the Philippines makes it a vast source of renewable energy and salt water. This paves the way for renewable desalination, which could aid in providing clean and accessible basic services to our remote communities. The goal of this study is to find the most economically and environmentally sustainable energy and water cogeneration system for selected remote island communities in the Philippines. Off-grid islands with populations less than 10,000 will be used as a basis for small-scale remote island communities in the country. The off-grid communities of Cabra Occidental Mindoro, Limasawa Leyte, and Almagro Samar were selected for this study. The specific objectives of the study are the following. 1. Provide optimized models of energy and water cogeneration systems for different future case scenarios using Homer Pro and Wave. 2. Determine the most economical option per future case scenario using life cycle costing. 3. Perform life cycle impact analysis, or LCIA, on the optimized future case models. And 4. Select the most environmentally sustainable option for each island using multi-criterion decision analysis, or MCDA. The electricity and water demand are based on projection and forecast calculations up until 2030. Population projections were calculated through the annual growth rate of the 2015 population census and the 2020 projection data of the Philippine Statistics Agency. The electricity demand of the islands was sourced from the NPC Small Power Utilities Group and projected to 2030, using the average year-on-year growth rate of the energy sales data from 2010 to 2017. Water projections were calculated through the demand forecast method of the Rural Water Supply Design Manual published by the World Bank. All water and electricity demand projections showcase a steady increase over the years, except for the electricity demand in Limasawa Island, where the growth is seemingly exponential. This is due to the Department of Energy electrification projects in Limasawa in 2017, which dramatically increased the energy production, consumption, and consequently, the average year-on-year growth of electricity demand in the island. The methodology will proceed as follows. First is the goal and scope definition of the study, to be followed by the assessment of the current situation using LCC and LCIA. Next, we'll define the future case scenarios, to be followed by the system design for energy and water cogeneration using Homer Pro and Wave. The assessment of future case scenarios using LCC and LCIA is next. And lastly, we will perform the multi-criterion decision analysis, or MCDA. For all future case scenarios in this study, it was assumed that desalination will serve as the primary source of water by 2030. It was paired up with different energy generation configurations, which are defined as follows. Business as usual, which assumes that the remote community will maintain its full reliance on fuel-based energy generating system. Transition, where a fraction of the generation mix coming from conventional diesel-fired power generation plants will be taken over by renewable energy plants. And lastly, independent, where the community attains an independent supply of power coming from renewables. Homer Pro simulations were used to determine the energy system architecture that is most apt for the islands. The study simulated a seawater reverse osmosis desalination plant using Wave software for water treatment plant design by DuPont to determine the electricity requirements of desalination. In the Homer Pro simulation, the average electricity demand of the island is considered as the system's primary load, while the desalination demand is treated as the deferrable load. All cost data that were used are projected to the 2030 value, with an average photovoltaic capital cost of $587 per kilowatt and an average wind turbine cost of $1,057 per kilowatt, as presented by IRENA. From the simulation results, the study selected energy systems with the lowest cost of electricity for the business as usual, transition, and independent cases. The business as usual scenario is intuitively 100% powered by diesel. The transition scenario limits the generation of diesel-fueled energy to only 2 to 3% of the total production capacity for all islands. The independent scenario shows that solar PV energy leads the capacity mix for the islands when the system is powered by 100% renewable energy. The high penetration of PV across all remote communities may be attributed to Homer Pro's algorithm of cost minimization while efficiently serving the required load. Life cycle costing is a prerequisite in evaluating the economic sustainability of the cogeneration of renewable energy and water in all islands. In this study, the total life cycle costs, or LCC, of all utilities come from the levelized cost of electricity, or LCOE, and the levelized cost of water, or LCOW. Using cost estimation values from Irena, Aberilla et al., Caldera and Breyer, and the cost of electricity produced by Homer Pro, the LCOE and the LCOW was calculated for all cases by analyzing the capital costs, utility costs, and operation and maintenance costs of the system. The results show that the business as usual case has the highest LCC across all remote communities. This is attributed from the high operating costs brought about by the sole use of diesel as the power source. The transition and the independent scenario LCCs are relatively closer in value, but the transition scenario gives the lowest LCC value. The high capital cost of 100% renewable energy is one cause of the higher LCC output of the independent scenario.
For the life cycle assessment, the data used to model the utility systems for the current and future scenarios, done in CIMAPRO 9.1.1.7, came from various inventory sources backed by EcoInvent 3.6. The estimation of environmental impacts were calculated using recipe hierarchies version 1.13 method, with 18 midpoint impact categories grouped by the environmental issue that they cause as shown in the figure. The scope of this life cycle assessment is from cradle to grave, which was comprised of raw material extraction, assembly, installation, transport, operation, maintenance, and eventual end life of the system's facilities. The analysis was based on a functional unit defined as the annual demand of energy and water of the island community. The results from the life cycle impact assessment of the three islands have shown that the highly diesel-reliant current case and business-as-usual scenario have the highest environmental impacts for most of the categories. Their high carbon emission increases their climate change potential, as well as their contribution to the air pollution factors such as ozone depletion, particulate matter formation, and the photochemical oxidant formation. These emissions can also contribute to the acidification of terrestrial and water bodies. Fossil depletion and natural land transformation were among the other categories where the current and business-as-usual case dominate. For the case of Cabra Island, the sole island with a relatively low electricity and water demand, the infrastructure of the energy generation system contributed most of the impacts, ranging to up to 84% at some categories. It is also notable that even the renewable energy-based transition and independent scenarios happen to have greater impacts than the other diesel-reliant cases. These can be seen in the following categories. On the water depletion category, due to the demand of wash water for solar photovoltaic systems, and the metal depletion category, due to the production of photovoltaic cells, and on the land occupation categories, due to the mounting of the PV plant. The Almagro Island has shown the effect of a significant increase of community water demand in the total environmental impact of the utility cogeneration system. The contribution of seawater desalination significantly took up most of the impacts, ranging up to 97%. The contribution of reverse osmosis desalination chemicals ramped up the impact value of seawater desalination for most of the impact categories, ranging from 90 to 99%. Ecotoxicity values for the transition and independent scenarios were also found to be greater than the impacts of the other scenarios. This is due to the increase of the reverse osmosis desalination chemical requirement, the energy needed for seawater desalination, and the treatment of scrap copper in the ferrous metal recycling process. Limasawa Island's recent electrification and industrialization caused an increase in projected power demand for the island in 2030. The analysis for this scenario has shown the great disparity between the impacts of a fuel-based energy grid versus a renewable-based, as shown below. The demand for fuel increases along with the community's power demand, thus significantly increasing the impacts of a fuel-reliant scenario at a factor of 10, compared to other scenarios for some impact categories in this analysis. Impacts due to generator fuel was found out to contribute approximately 90% of the total category impact for diesel generation systems. The increase in power demand due to the industrialization tend to increase the impacts due to the photovoltaic system of independent and transition case scenarios. To determine the most environmentally sustainable future scenario, a multi-criterion decision analysis using Vickers method was performed on all islands. Two weighing schemes were implemented on the analysis, an equal weighing among impact categories and an environmental footprint weighing based on the standards provided by the European Union. The results have shown that the transition case to be the most environmentally sustainable option obtaining the lowest Q value for both weighing schemes for all islands. With the highest weigh factors allocated to the climate change, air pollution, and resource depletion categories for environmental footprint weighing, the business as usual scenario ranked lowest due to its dependency on fossil fuel and high carbon emissions. A compromise set was determined when using the environmental footprint weighing scheme, comprised of the transition and the independent scenarios. This meant that there is no significant advantage among the two options in terms of environmental sustainability, and both can be considered as best scenarios. The result of the sensitivity analysis for the economic sustainability of the future options for the three remote islands have shown to favor the transition scenario at lower weighing values for the annualized capital cost, while it favors the business as usual scenario at higher annual capital cost weighing values. A compromise set which includes the independent and transition scenarios are established on lower annualized capital cost weighing values due to the high capital cost of renewable energy systems. Meanwhile, for high annualized capital cost weighing values, generator systems are favored due to its cheaper capital cost along with its high cost of operation and maintenance due to its fuel requirements. Finally, a sensitivity analysis to obtain the overall sustainability score of the future case scenarios was done to determine the best case for each island. Implementing the two weighing schemes for each island, it was found out that the transition scenario dominated among the different future case scenarios. Using the environmental footprint weighing scheme as shown at the lower graphs, the transition scenario obtained the lowest overall sustainability score for all weighing values, with the independent case entering the compromise set at the environmental sustainability weighing values of 0.7 and higher.
For our conclusions, all the three studied remote island communities have shown favor on the installation of a photovoltaic, wind turbine, diesel generator, and desalination system in terms of the lowest cost of electricity, as optimized by Wave and Homer Pro. The life cycle costing results show that the transition scenario produces the lowest life cycle cost across all islands. The high levelized cost of electricity of the independent scenario exceeds that of the transition scenario, which leads to the persistent but fractional use of diesel generators at around 2 to 3%.
Also, the transition scenario was found out to be the most environmentally sustainable option due to its lower impact yields among the different future scenario options. A compromise set composed of the transition and the independent scenarios were found to be the economical options for a lower annualized capital cost weighing, while the business as usual scenario serving as the best option for higher annualized capital cost weighing. Finally, the transition scenario was found out to be the best option in terms of economical and environmental sustainability, with the independent scenario joining the compromise set at a higher environmental sustainability weighting.
For our recommendations, we suggest performing a sensitivity study on the transition scenario using Homer Pro, specifically on the contribution of the diesel generator in the production capacity mix. We also recommend conducting a sensitivity analysis on the capital costs of renewable energy systems during life cycle costing.
We also recommend to conduct sensitivity analysis on various system optimization factors, such as fuel price projections and electricity and water demand. Lastly, perform social sustainability studies on these islands to have a better perspective on the overall sustainability of the systems under study.
Thank you for your presentation. Any question from the audience and panel? Isa?
Sir, no questions here naman. Pero comment lang sa presentation. We cannot see the figures properly kasi liit na nung font and maliit na masyado yung figure. Pero yeah, good job. Wala akong comments po. Wala akong questions.
Okay, sige. I have a question.
Thank you, sir.
You have mentioned the cost of electricity and other costing dun sa presentation nyo, and you use some models ba yun? Earlier developed? Ano yung ginamit nyo again for the cost of ano ulit yung ginamit nyo for the calculation of cost of electricity?
Sir, for the life cycle costing, we use the cost of electricity developed by Homer Pro. So the software actually generates the cost of electricity, which we could use to determine the annualized capital cost of the system. But for the cost of electricity, we used yung simulation results. While for the cost of water, we use the wave software for desalination. And then we computed the electricity demand using the software. And then using the cost of electricity generated by Homer, computed the cost of water of the system, sir.
So, dun sa Homer, is it normalized calculation regardless of the area, or does it have a adjustment component in terms of dun sa Philippine setting?
Sir, the calculations are normalized, but the specifications of the system are specific to the island itself. For example, the electricity demand or the electricity demand of the community or the electricity demand of the water generation. All demand data were sourced from actual data or actual community data from the Department of Energy and from the Philippine Statistics Agency.
Okay. So, so there's a good confidence level on the model
Yes,
na ginamit dun sa calculation. Okay. Kasi like there's a big difference, especially kahit lang dun sa cost of electricity between different countries kasi, 'di ba? Magkaiba sila in terms of there are countries that have cheaper electricity, there are countries that have more expensive electricity. So I was just curious kung paano nakuha yun. And you have mentioned naman that
So we
those
also use
local data were taken into account. You
yes,
also
sir.
use what?
We also used exact coordinates in the island to determine the energy data. So while the computation system of Homer is generalized, the settings of the simulation are very specific to the island itself.
So there's a question from a panel member, Dr. Brian Alaman. Are Homer Pro and Wave open access ba sila?
For Homer Pro, we use the free trial version. So it's not open access, but we had 21 days to complete our simulations. While for the Wave simulation by DuPont, it's actually free access and free to download.
Okay. I was also curious din ako kung ano yung basis nyo in choosing the 3 islands.
All right, sir. So actually, we looked into the islands of the off-grid islands of the Philippines. So the first limitation that we had was the island has to be off-grid, mainly because we're trying to generate electricity and water in islands where the local services could not reach, basically. So when we determined the off-grid islands that we should consider, we also looked into the water demand and the population demand. So for example, we chose as specified in the study, we chose the populations of less than 10,000 because it actually affects the cost of electricity because it's proportional essentially. But aside from that, how we selected studies that are, for example, for the Cabra Island, it's the average. It's something that we could consider as the average island with the average demand for water and the average demand for electricity. Whereas for the Limasawa Island, the water demand is proportional, but the electricity demand is kind of higher than normal because of the electrification projects in Limasawa. While for Almagro, we chose an island that has a normal or average electricity demand, but a high water demand due to the livestock industry that is prominent in Almagro. So that was the method of selection of the islands that we had.
So ginagamit ba nila yung agricultural waste in generating energy?
Sir, currently, DOE has not listed any renewable energy DPP power plants in the off-grid islands of Almagro and Cabra, although a solar power plant is already present in Limasawa.
Okay. So dun sa recommendation nyo, you have mentioned that transition is the best in terms of economic and sustainable scores, right? Yung Q scores. How do you define the transition? Like, gaano katagal yung transition before we move into the independent case?
Okay, sir. First, let me define our future case scenario. So, yung paraan po namin ng pag-analyze dito sa mga future scenarios na ito ay per year impact. So, it is out of our scope to measure yung total impact from the present up to 2030. We're looking on the annual production of power and water, as well as the annual impacts generated by these systems in these islands. So, ayun. So, let me just clarify yung scope po namin. So, it's the annual impact and annual generation of electricity and water. Tapos, about the transition case scenario, on the selection of these scenarios, we will look at the different simulations coming from Homer Pro. So it generated different configurations of RE plus fuel generators plus batteries doon sa Homer simulations natin. So for the transition, we look at which models ni Homer ang merong RE plus fuel generator plus batteries. So that will na pinakamura in terms of the cost of electricity na ginagawa nung system na yon. So that will be our transition case scenarios. For the independent, we only look at the those models generated by Homer, which was consist of purely renewable energy. So photovoltaic plus wind turbine plus batteries. So ito ay wala ng fuel generators na kasama dun sa system. So for the model, yung alin yung pinakamura na model, yun yung tinatag namin as the independent scenario na pinutuloy namin ng life cycle costing and life cycle impact analysis. So yun ay pagtingin dun sa economics and environmental sustainability ng ating mga systems respectively.
Okay, so yung data nyo is 1 year of parang kapag ganun yung energy source nung island na yun.
Yes, sir. Pero
for 1 year.
It's annualized actually. For example, we look at our assemblies actually. Yung assemblies namin ay tinitignan niya yung impacts nung for the whole lifetime of a specific technology. For example, the fuel generator. When we establish the fuel generator assembly in CIMA Pro for the environmental impact simulation, yung sa assembly, it considers yung 30-year lifetime ng ating fuel generator. Pero when we input the data, we only account for yung annualized production ng kuryente using a fuel generator set. So kumbaga, yung 30 years ni generator set, yung buong impacts niya, dinivide namin, yung buong impacts ni fuel generator for the whole 30 years, dinivide namin by 30. Ganun siya
Okay.
kina-calculate ni CIMA Pro. So same for the rest of the technologies using the different models that we had. Ganon. So, kumbaga, kinilalump namin yung impacts generated from these technologies as well as the production of these technologies, yung downstream and upstream process from the raw material extraction down to the end life of these technologies, assemblies. Ayun, sir.
Okay, thank you. Now I understand more. All right.
Sir, like the DOE...
Time's up na yung
okay, sir.
Q&A natin. Can you, yung additional answer, can you supply it through the chat para malaman din iba?
Sir, it's just additional context. It's not actually related to the answer, sir. So, but okay,
Okay lang. Just type it in the chat kasi time's up na tayo. All right, let's go to the next pair. Mr. Petro and Ms. Miranda. Their thesis title is Assessing Sustainability of Rice Production in the Philippines Using Life Cycle Analysis. Okay, let's start.
Okay, let's start. Good day, everyone. I am Calista Miranda, and this is Simon Pecho. And today we will be talking about food and sustainability. In particular, we will be assessing the sustainability of rice production in the Philippines using life cycle analysis. Next slide, please. Next slide. First, we'll be giving you a bit of background on the subject. With this, we'll be able to show you the motivation for our study. Given that sustainability is a very broad subject, we'll need to narrow it down to a workable scope before we go into the process itself. We're going to conclude our presentation with recommendation for future studies. So, formerly an agricultural country, the Philippines is quickly becoming more industrialized, choosing instead to strengthen its service sector. Though that may be the case, the Philippines is still the 8th largest producer of milled rice in the whole world. As a key player in this industry, it is important to invest in this field of study so that we may be able to limit its environmental impact and therefore promote a more sustainable production. Next slide, please. To support this assertion, let's look at some statistics from our world in data. According to the January 2020 report, agriculture serves as one of the top contributors to global warming. Land use. About half of the world's habitable land is actually used for agriculture. Water consumption, here the paragraph in the middle, 70% of freshwater withdrawals is used for the same purposes. Greenhouse gas emissions, about 26% of greenhouse gas emissions is actually due to food production. Owing such great contributions to global warming, it is important, therefore, to push this field's development to a more environmentally conscious one. Doing so would also help the world achieve its global goals in this respect. Next slide, please. These goals, which also come in the form of the Paris Agreement, made way back in 2015, ensure not only the habitability of our planet, but also the quality of life it can support. The Paris Agreement's goal is to limit the global warming temperature increase to well below 2 degrees Celsius, preferably to 1.5 degrees Celsius, beyond which the planet will face natural disasters on a catastrophic scale, as well as chain reactions of various natural phenomena which will eventually leave the planet unable to support life. Next slide, please. To pursue these goals, we must make radical improvements in our way of living. Life cycle assessment is a great tool for this purpose. LCAs essentially evaluate the environmental impact associated with a certain product or process. Next slide, please. But one of the things that should be kept in mind is that sustainability involves the overlapping of many different factors. There's the environmental, social, political, economic, and personal levels to it, all of which we must juggle. But as a study from the Journal of Business Ethics finds, focusing on the environmental and social aspects of development during design with less primacy on its profitability is a step towards better achieving sustainability goals. Next slide, please. In creating this life cycle analysis, the following things were considered. First, a cradle-to-gate analysis was performed. That is, the study will limit the scope only to the actual production of rice, from its planting to its harvesting. Researchers relied on statistical reports, particularly from PalaiStat, in making their simulations. Straw management, a key process in the post-production of rice, was left out of the study. Let's now proceed to our methodology. To you, Simon.
So for our methodology, we first define the scope of our process, which is first, manufacturing of fertilizers, pesticides, and machineries used in the process. Then we identify the process flow, which is how these fertilizers and pesticides are linked from their providers. Then we gather data using statistical values from PaleyStat, and other literatures as well. Then we proceeded with database gathering, wherein we used EcoInvent 3.7 APOS allocation by substitution to fill in our background data with proxy values from EcoInvent. Then we simulated the data using the foreground data via OpenLCA. Then we assess the impact of growth production using 1 kilogram of paddy as functional unit. Then afterwards, we interpreted the data based from our results. So for the assumptions, we assume that the rice production undergoes irrigated conditions because rice fed, although it's the second commonly used source of water, is still dominated with irrigated conditions. Then we also used inbred seeds because it is the most commonly used type of seed. Also, we assumed that no organic fertilizer was used due to lack of data. Instead, we used NPK, but instead of directly using NPK, we used urea, ammonium sulfate, ammonium phosphate, and the complete form, which is assumed to be 15-15-15. Now for the inputs, we used the yield, which is roughly 4,000 kilograms per hectare. That's the average yield from 2010 to 2020. Then, like what I've said earlier, we used urea, ammonium sulfate, ammonium phosphate, and a complete form. For the pesticides, we used cypermethrin, glyphosate, propiconazole, and 2,4-D because they're the most commonly used pesticides. So we based it from the percent of farmers, a distribution of farmers who use such pesticides. Then, like what I've said earlier, we used EcoInvent as background. It's used for machine operations. The data from the machine operation was used, and the emissions were in. We used ratio. The ratio of the yield from EcoInvent, which is roughly 6,000 kilograms per hectare, and the yield in the Philippines, to balance the value with the Philippine setting. Now for the results, we use recipe midpoint H. So H stands for hierarchist. So this model assumes that the analysis is based from a policy and it's within 100 years, unlike the other type of recipe midpoint, which are individualist. It's for a short, it assumes that it's for longer period of time. For the growth process, we obtain the following results. It has significant contribution to marine eutrophication, global warming, terrestrial acidification, human non-carcinogenic toxicity, freshwater eutrophication, and freshwater toxicity. Now for cypermethrin, we obtained roughly negative times 10 to the negative 6 of magnitude, but it is still the most significant. Its flow is still considered as the most significant in terrestrial ecotoxicity. So for our conclusion, we found out in our simulation that mostly nitrogen, the emission of nitrogen, the emission of phosphorus, and even the emission of heavy metals play significant impact because they are usually found in the manufacturing of fertilizers and pesticides. And also the pesticides as well, like what I've said earlier, the cypermethrin. So with that, even though we can say that we can reduce the number of fertilizer and pesticide, but we must also take into account that if we reduce the number of pesticides, we can decrease the yield. So what can we propose? What can we propose? We can propose other alternative fertilizer and pesticides. So for our recommendations, we recommend to use cradle to grave, which means instead of just assuming that the output is paddy, we'll then stretch up to milled rice and as much as possible straw rice and assess and analyze its waste treatment and other waste treatment methods in straw rice. Then we can also conduct life cycle cost analysis and lastly sensitivity analysis to analyze different types of processes. We can analyze rain-fed versus irrigated systems and other or different types of fertilizers, etc. So that's it for our presentation. Thank you very much.
Okay, thank you for the presentation. Walang medyo choppy yung presentation. Is there anyone in the audience or panel that has questions to the presenter? Isaac, sir, Bright.
Hi, so since medyo choppy nga yung presentation, baka pwedeng i-run down nyo lang kami quickly sa conclusions ng study nyo.
So for our study po, we weren't able beforehand to present the contributions of the different processes in rice production, such as yung application ng type of fertilizers, pesticides, yung irrigation din po, but we were able to present the general impact categories for growth process, which are based from the emissions of the growth process. So these emissions can be found in, pwede rin po sila ma-release sa air, sa water, tapos may corresponding impacts po sila. Like sa toxicity, for example, meron kaming result na yung heavy metals po yung mataas po yung contribution, yung emission ng heavy metals. As for water consumption, water din po yung mataas. Pero for the growth process, negative po yung lumabas since it's assumed na hindi na deplete yung water. So parang yun po. Okay. Then ang nakuha rin po namin yung global warming po, may low value po siya since we assumed na wala pong ginamit na organic fertilizer. Pag may ginamit po ng organic fertilizer, magkakaroon po ng methane emissions po. Tapos for eutrophication, may significant effect po yung emissions from nitrates and phosphorus na nanggagaling po sa fertilizers po.
Okay, sir. Thank you. Sir?
Okay. Yung data na ginamit nyo galing sa Palestat?
Opo, sir. Bali, ano po siya?
Anong range nung date from what year to? Ano yung scope ng data na ginamit from Palestat?
Since in other data po sa Palestat, we assume na from 2010 to 2020, yung iba pong data na nakuha namin na based from a survey then conducted by Palestat, they're instead from 2011 to 2012 since they're the latest na po from Palestat. Due to we opt po for surveying po yung Palestat if ever they had newer surveys po, but may limitations din po kami na they weren't able to provide us interviews po due to some of their employees having COVID-19 din po. So we just resorted to statistical data from Palestat.
Yeah, what's the limitation of the data from the Palestat indicate? Was it na-indicate pa yun sa manuscript niyo?
Yes, sir.
Okay, and you have mentioned that you did some simplification with in terms of doing the LCA. So if ever that merong access kayo from that kind of data, anong mga factor yon that will increase the accuracy of your LCA? Ano yung mga inalis nyo? May mga factor kayo na inalis that aside from that organic fertilizer, meron pa ba kayong inalis na mga factor na hindi nyo na kinonsider given na wala kayong data? Meron ba?
Few other factors po na typically there's like dalawang type. There's irrigated system and there's the other yung rain fed system. So since masyado magkaiba yung type of data nila, we had to choose between one of them. So we chose the irrigated system kasi mas common sila in the Philippines. Another limitation it just raised in a previous webinar then is yung existence of yung hybrid system. So it's a combination of the irrigated system and yung rain-fed system. So isa yun sa mga hindi namin na-consider. And in future studies, we'd like to recommend yung sensitivity analysis considering those two other systems in water management.
Okay. Sige. Siguro final question here from Sir Brian. Would it be possible to relate the insights from your work to assess the impact on surface water quality in agricultural land areas? Could you comment on that? And can we use to generate an enabling recommendation to manage impacts of excessive nutrients in nearby bodies of water close to these agricultural sites?
Yes po. So one of yung impact categories that we decided to report then po, and one yung more significant impact categories in our study is yung marine and freshwater eutrophication and also yung ecotoxicity. So given that sinet naman din kasi namin yung kind of yung kind of systems that we're able to that we were working with in future studies, pwedeng paggamit, yun nga, yung doon papasok kasi yung sensitivity analysis. So, pwedeng ng iba kind of data. Since yun nga, limited din kasi yung the kind of data that we are working with. Para ma-measure din yung type of and yun natin kasi assess. So as ayun, pero ano kasi
Copy ba yung sound?
Hello?
Can you just write your answer again in the chat? Kasi hindi ko alam kung sa akin lang, but napawala kasi yung answer. So we can move on and then just write the answer dun sa chat para lang mabasa, para lang malaman din ng iba. Just write it in the chat so we can move on. Kasi time na. Okay. So let's go to the last pair. Their title, the thesis title is Sustainability Analysis of Road Transportation Fuel Scenarios in the Philippines. So let's welcome the presentation of Ms. Talan and Ms. Terrado. Right?
For our undergraduate thesis, we will be presenting a sustainability analysis of road transportation fuel scenarios in the Philippines. I am Fatima Talan.
And I am Nikki Terrado.
Here is a brief overview of our presentation. We will discuss the background of the study, the results, and finally, the conclusion. First, the background. According to the Department of Environment and Natural Resources, in 2019, 74% of the air pollutants came from mobile sources. Out of the whole transportation sector's oil demand, 88.2% came from the road transport, and 89.9% of the fuel consumed by the transport sector is composed of diesel and gasoline. One policy that has been implemented to address these issues is the Biofuels Act of 2006, which dictates that biofuel blends must be composed of 2% biodiesel or B2 and 10% bioethanol or E10 by volume, and this facilitates the use of locally produced biofuel blends. Another initiative, kick-started in 2017 by the Department of Transportation, is the Public Utility Vehicle Modernization Program, which will replace traditional PUVs with units that have at least Euro 4 engines or are electric-powered. For the long term, the Philippine Energy Plan 2018 to 2040 of the Department of Energy presents two scenarios for the year 2040: the business as usual or BAU scenario and the clean energy scenario or CES. The BAU assumes that parameters of the current scenario are maintained, but the installed capacity of renewable energy will increase up to 20,000 megawatts. The CES assumes that 10% of the motorcycle, car, and jeepney fleets in 2040 will be electrified. The share of renewables in the mix are also assumed to increase. Segmentation of the energy mix for the two scenarios can be seen in the following figures. However, these existing schemes prove to be lacking because of the rate at which they are implemented and revised. Some policies are also outdated relative to the fuel industry's growth. Sustainability analysis tools such as the Life Cycle Assessment or LCA can help determine which aspects of our fuel industry needs improvements. Well-to-wheel LCA studies will highlight the trade-offs posed by the shift to alternative fuels and the importance of considering the complete fuel life cycle. These kinds of studies benefit greatly from extensive databases with the latest data, but unfortunately, local databases on the road transport sector are very insufficient. That being said, This study aims to analyze road transport fuel scenarios in the Philippines through the specified methodology and evaluate them based on environmental sustainability indicators in a life cycle assessment.
To do so, we first characterize the current road transportation fuel scenario in the Philippines. We then evaluate the environmental sustainability of the current scenario. We also evaluate and compare the environmental sustainabilities of the BAU and CES proposed by the DOE in their energy plan. The scope or system boundaries of the study can be seen here. For the life cycle of electric vehicles and electricity generation, the current and 2040 power generation mixes of the Philippines were considered. The functional unit for all factors is 1 kilometer traveled by each vehicle or 1 vehicle kilometer. The life cycle inventories are based on the existing processes in EcoInvent. The best available data from literature sources were used wherever applicable. Results gathered from the LCI were translated into indicator values using the recipe model. These indicators, which we will discuss as we go through the results, were classified into these environmental effects. Modeling of the LCA performed in CIMAPRO, and the results we gathered will now be discussed. In order to streamline the discussion, for each vehicle type, we'll be showing the results for the conventional fuel used by a majority of the registered units. This will be compared to a most promising fuel in terms of impact indicators. For the next few slides, such as this one, impacts with the highest values will be highlighted. Having a 100% global warming potential means that E10 gasoline had the highest GWP among all the fuel types studied for cars. In turn, CNG had a value around 30% lower than that of E10 gasoline. An observed trend for most E10 gasoline and B2 diesel fueled vehicles was that these fuels had significantly higher emissions contributing to air pollution. This is evidenced by the ozone depletion potential, the ozone formation potentials, and the fine particulate matter formation potential. These air pollution impacts are indicated by CFCs, nitrogen oxides, and particulate matter emissions. For all vehicle types, E10 gas also had the highest land occupation potential, and 93 to 98% of these values stem from the fuel manufacturing process. A similar trend was also noted for the water consumption potential of E10 gas. The fuel manufacturing process also accounted for 60 to 88% of water consumption. For most impacts in SUVs, such as the ecotoxicity and some resource scarcity potentials, CNG did not fall far behind from B2 diesel. However, CNG was found to consume much less fossil fuel resources compared to B2 diesel and E10 gas. The utility vehicle fleet is comprised of various vehicle models, including B2 diesel fueled jeepneys. For UVs, B2 diesel had the highest global warming potential, and it is about 5 times higher than that of CNG. Its impacts on air pollution are also much higher than that of CNG. Although not seen here, the E10 gas UV had the highest terrestrial acidity potential, more than 56% of which is attributed to the transport use phase. Here we can see the B2 diesel for trucks having significantly higher impacts towards air pollution. It is also once again observed to have a significantly high value of terrestrial acidification potential. As observed in other vehicles, B2 diesel also has a much higher fossil fuel resource scarcity potential. The impacts of bus fuels in each indicator are close or within the same order of magnitude, as evidenced by the toxicity potentials here. However, once again, land occupation potentials of B2 diesel and CNG fall far behind that of E10 gas, and the fossil fuel resource consumption of B2 diesel is much higher than that of CNG. Here we see the ionizing radiation potential of E10 gasoline. Along with that of B2 diesel, it is much higher than other fuel types in most vehicles. This is due to the fuel production phase. E10 gas also has the highest marine eutrophication potential out of all the fuel types. Almost all, or more than 94% of this MEP is coming from the bioethanol blended gasoline production process. The previously mentioned high resource scarcity impacts of E10 gas are also evident in this figure. For tricycles, only 2 fuel types were considered. The impacts of E10 gas towards air pollution are still observed, but the electric vehicle is not falling far behind in terms of contribution to climate change effects. It can be observed that electricity has very high impacts with regards to eutrophication, ecotoxicity, and damages to human health. More than 40% of the electric tricycle's impact to freshwater eutrophication comes from electricity production. Meanwhile, the assembly stages of the battery and the EV itself contribute greatly to the human toxicity and ecotoxicity impacts of all electrified vehicles. The mineral resource scarcity potential of motorcycles and tricycles shared a similar trend with their ecotoxicity impacts, such that EVs had the highest values, mostly coming from the mineral-intensive electricity generation and battery production stages. After getting the impacts of individual vehicle fuel combinations, we applied them into the current fleet mix of the Philippines to study the scenario. As you can see here, more than half of the country's vehicle fleet is composed of motorcycles. One of the indicators we previously mentioned is the global warming potential under the environmental effect of climate change. It was measured using the equivalent amount of carbon dioxide emissions by all the vehicle fuel combinations. Here we can see that although motorcycles make up more than half of the fleet, the utility vehicles contributed to 40% of the equivalent carbon dioxide emissions. Here we can see that the utility vehicles also accounted for almost 60% of the fleet's total fossil resource consumption, which is around 1.2 million equivalent kilograms of oil. It is also worth mentioning that for 15 out of 18 indicators, UVs had the highest shares, while cars dominated the rest.
With all the results from our simulations, these are the key findings that we have gathered. First, in general, fuel production and use phase processes significantly contribute to the impacts. These are equivalent to electricity generation, battery production, and vehicle assembly for the EVs. Secondly, conventional fuels have the highest impacts in most indicators. And among all the fuels, CNG has the least impacts. Environmental burden shifting can happen with electric vehicle penetration because of its toxicity impacts. For the BAU, if we retain the dominant use of conventional fuels and mandated biofuel blends, the indicators with detrimental impacts as mentioned earlier in the current scenario will also be observed in 2040. Reliance on coal and fossil fuels for electricity production indirectly adds to the impacts through the manufacturing processes. Lastly, fleet mix is mostly composed of internal combustion engines, hence there is no significant improvement. Overall, the magnitude of impacts for each indicator is 9 to 17 times higher than the current scenario. For the clean energy scenario, increasing biofuel blends did not show any desired improvement in most indicators. For instance, water consumption potential for the CES E20 gas is 68 to 398% higher than BAU E10 gas. On the other hand, E20 gas land use potential is 93 to 622% greater than the E10 blend from BAU. Secondly, electric vehicles had significantly lesser impacts for all vehicle types by adding more renewables to the energy mix. And lastly, use phase emissions decreased because of the fleet penetration of electric vehicles, but impacts from conventional fuels counteracted this. For the conclusion of the study, importing fuels significantly contributes to the environmental burden of fuel production. The rate at which we are replacing conventional fuel and energy sources is very much slower compared to the rate of fleet population increase. Lastly, EVs eliminate tailpipe emissions, but the potential for ecotoxicity and human toxicity would be so much higher. These are our recommendations based on the conclusion of the study. Electric vehicle programs must be strategically done. This entails adoption of more renewable energy technologies beforehand. Without this, aggregate emissions would surely occur in the electricity generation phase. Metal reserves would also be affected. Therefore, joint planning between EV development and involved metal industry sectors should be considered. Developing EVs to have longer lifetime mileages would also lessen the stress on our geological reserves. Reliance on imported petroleum products and biofuels should also be decreased. Various possible feedstock for biofuel production can be incorporated to reduce our importation. Large-scale programs for CNG and LPG use in transport must also be encouraged. Investing in the exploration of more natural gas reserves should be considered because other studies have also proven that these fuels have lesser environmental impacts than conventional fuels. For the future works related to ours, we recommend to experiment on the possible feedstock mix for the future scenarios. The changes due to vehicle technology improvements, like its emission factors, should also be incorporated in the life cycle assessment. New infrastructure emissions like charging stations for EVs must also be taken into account. Lastly, the socioeconomic impacts of projects must be assessed as well so we can prevent any kind of economic displacement within the transport sector. That is all for our presentation. Thank you.
Right. Thank you for the presentation. Yeah, turn on your videos. Meron bang may tanong sa audience? Panel?
Sir, wala naman pong questions here.
Okay. I'm just interested dun sa comparison nyo nung may water consumption. Mas mataas si ano. Can you go back to that slide? Paano
Yes
ulit
po,
na-count
sir.
yung water consumption?
Oh, I can't screen share po. May I
You
share
can
the
screen
slide?
share.
Ayan,
Co-host
okay.
ka na.
Yes, wait. Is it showing na po? Water consumption for which vehicle po?
Yeah, you can just i-browse natin. Saan na ulit yun? Yung may graph ng ano,
okay.
ng comparison.
Here po.
Yeah.
Okay.
So, paano ulit na-determine itong water consumption?
Yung water consumption po, yung definition niya dun sa database that we use, it's the cubic meters of water consumed per cubic meters of water it's consumed versus extracted po nung process. Opo.
Yeah, so saan galing yung water?
Oh, this is actually mostly due to the fuel production phase po. Kasi ethane gas is highly reliant on, as mentioned, it is 10% by volume bioethanol, and for that, merong plantations for the production of bioethanol, particularly in the Philippines, which is sugarcane. So the water consumption for this is particularly high because in this part, we actually evaluated the overall emissions. So we've taken into account all the motorcycles that exist in the Philippines as recorded in the data of LTO, and we computed the total water consumption of each fuel type under that vehicle type.
Okay. So from yung pinaka-ethanol production, okay, I get it now. Yung sa electric vehicle, yung mix ba ng ginagamit nating electricity ng source of electricity for the electric vehicle, was that taken into account?
Yes po. In the current scenario, we modeled it according to the current energy mix of the Philippines. And for the future scenarios, we also have taken into account their projected energy mixes for the Philippines, as indicated in the DOE Philippine Energy Report, Philippine Energy Plan, for 2018 to 2040.
Okay. So itong 99.9% of fleet,
yes.
Anong fleet ito again? Sorry if I missed it.
This means po na 99.9% of our tricycle fleet runs on E10 gas po. Yun po siya.
Okay. I have no further question. Okay.
Thank you for your questions.
From the other panelists.
Yeah, if meron pa bang may question? Yeah, if wala na, okay, good job everyone. And let's, ano lang muna tayo, photo off muna tayo. Mga participants, can you please turn on your videos, your cameras para sa quick photo off lang. Sir Mike? Pwede ba ikaw magkumuha ng picture?
Sir, ako po, sir. Ako daw po kukuha.
Okay, ikaw. Sige. Alright, sige, count ka na lang.
Okay, so 3. Pa-on na lang po ng mga cams. Wait. So, 3, 2, 1. Okay na po.
Alright, so ang natitira na lang is yung announcement ng best presentation. So just give me a minute or two para makipag-usap sa ibang panel kung sinong panalo. Wait lang. Ayan, so nakapag-vote na rin yung ibang panel. So congratulations to JMA1, Mr. Baginon and Salak, Mr. Salak. So you have won the best presentation for this parallel session. Oh, congratulations. And then later, dun sa meeting, dun sa pinaka general Zoom natin, dun yung bigay ng certificates. So, move na ba tayo, Sir Mike?
Yes,
Move na ba tayo lahat
so
sa
yes, sir. So that concludes parallel session 7. That concludes your CHE 144 final thesis defense. Congratulations to everyone for successfully defending your thesis. So manuscript na lang. Okay, so advisors yan ang bahala dyan. And that's it. Good luck and good job, everyone. Thank you, Sir Ram. Thank you, Sir Isaac, and thank you, Sir Jude. Then dito ba? What is Sir Jude? Coming here. So thank you, everyone. Please proceed to the original parallel sessions, parallel session 1 for the awarding of the certificates. So thank you.
Thank you, Paul.